Langchain Google Vertex Callbacks. Description: Langchain Google Vertex AI callbacks are a powerful feature that allows you to monitor and debug your Langchain applications running on Google Vertex AI. These callbacks provide real-time insights into the execution process, enabling you to track progress, identify bottlenecks, and optimize performance. Inputs: Langchain application. The specific Langchain application or chain you are running on Google Vertex AI. This could be a simple chain, a complex pipeline, or a custom application. Google Vertex AI environment. The Google Vertex AI environment where your Langchain application is deployed. This environment includes resources like the Vertex AI endpoint, models, and data outputs, real-time logs, detailed logs about the execution of your Langchain application. These logs include information about the steps involved, input and output values, and any encountered errors, metrics and visualization metrics that provide insights into performance, resource utilization, and other aspects of your application. These metrics can be visualized in the form of graphs and dashboards for better understanding in analysis. Steps: initialization. When the Langchain application starts, the callback is initialized. It connects to the Google Vertex AI environment and prepares for logging and monitoring. Execution: monitoring throughout the application execution. The callback tracks the progress of each step, records input and output values, and gathers performance metrics. Error handling: if any errors occur during the execution, the callback captures the error details, including the error message, traceback, and context. Finalization: upon the completion of the application, the callback finalizes the logging and metrics collection process. It might generate reports or summaries to provide a comprehensive overview of the execution. Metrics: execution time, the time taken for each step and the overall application execution. Resource utilization: the amount of CPU, memory, and other resources consumed by the application. Model latency: the time taken for each model inference. Input and output sizes: the sizes of the inputs and outputs processed by the application. Error rates: the percentage of errors encountered during execution. Visualization plots: execution timeline, a visual representation of the execution process, showing the order and timing of different steps. Metric trends: graphs and charts that show how different metrics change over time. Error distribution: visualizations that illustrate the distribution of different types of errors. Resource utilization plots: graphs that show the CPU and memory usage patterns over time. Fine-tune parameters: logging level controls the verbosity of the logs. You can choose to log basic information, detailed information, or even debug level information. Metrics collection interval determines how frequently the callback gathers performance metrics. You can adjust this interval based on your needs. Visualization options allows you to customize the visualization plots, such as the types of graphs, colors, and display options. Uncertainty methods: confidence scores provide an estimate of the model's confidence in its predictions. Probability distributions present the probability of different possible outcomes for each prediction. Challenges and fixes: Challenge 1: excessive logging. Logging too much information can overwhelm your system and make it difficult to find critical insights. Sample use case that resulted in Challenge 1: logging every individual token during language generation. Fixes to Challenge 1: adjust the logging level to log only important information. Use filters to selectively log specific events or metrics. Challenge 2: inefficient metric collection. Collecting metrics too frequently can impact application performance. Sample use case that resulted in challenge 2 collecting metrics for every individual token in a large text processing task. Fixes to challenge 2 set the metric collection interval appropriately. Consider collecting metrics only for specific parts of the application or at strategic intervals. Challenge 3 difficulty in debugging errors. It can be challenging to diagnose errors based solely on log messages. Sample use case that resulted in challenge 3 an error occurs during a model inference, but the log message does not provide enough information about the cause. Fixes to challenge 3 include context information in log messages. Implement custom error handlers to provide more detailed information. Utilize debugging tools like breakpoints and logging statements within your code. Challenge 4 limited visualization capabilities. The default visualization options may not be sufficient for all needs. Sample use case that resulted in challenge 4 you need to analyze specific metrics over a long period to identify trends. Fixes to challenge 4 explore external visualization tools that integrate with Google Vertex AI. Customize the visualization plots using available parameters. Challenge 5 difficulty in integrating with other monitoring systems. It can be challenging to connect the callback data with other monitoring and alerting systems. Sample use case that resulted in challenge 5 you want to integrate the callback data with a centralized logging system or a monitoring dashboard. Fixes to challenge 5 use the available API endpoints to export callback data. Explore third-party integrations that bridge the gap between Google Vertex AI and other systems. Langchain Google Vertex Callbacks Vertex AI Callback Handler. Description: the Vertex AI Callback Handler is a Langchain callback that provides integration with Google Vertex AI. It's designed to track and manage the execution of Langchain chains within the Vertex AI environment. This callback allows you to monitor and log chain execution record events like chain start, end, and individual step execution, along with associated metadata. Log model inputs and outputs track the data flowing through your chain for analysis and debugging. Visualize chain execution. Optionally generate visualizations for your chain's execution flow and performance. Integrate with Vertex AI services. Leverage Vertex AI features for model training, deployment, and monitoring. Inputs: chain an instance of a Langchain chain that you want to track and manage. Projected optional: the Google Cloud Project ID where your Vertex AI resources are located. Region optional: the Vertex AI region where your resources reside. Experiment name optional: a unique name for your Vertex AI experiment. Run name optional: a unique name for your Vertex AI run within the experiment. Model name optional: the name of the Vertex AI model you are using. Logging level optional: controls the level of logging detail, e.g. info, debug. Enable visualization optional: a flag to enable visualization of chain execution. Outputs: execution logs records chain execution events. Model inputs and outputs, and associated metadata in your Vertex AI experiment. Visualization data optionally generates visualizations of chain execution flow and performance in your Vertex AI experiment. Steps: initialization: the callback initializes itself with the provided settings and connects to the specified Vertex AI environment. Chain execution tracking: it monitors the execution of the provided Langchain chain. Log event recording: it records chain start, end, step execution, and other events in the Vertex AI experiment. Data logging: it logs model inputs and outputs for each chain step. Visualization generation optionally generates visualizations of chain execution flow and performance. Integration with Vertex AI services enables interactions with Vertex AI models. Training and monitoring services. Metrics. Chain execution time tracks the duration of chain execution. Number of chain steps counts the number of steps executed within the chain. Model inference time records the time taken for model calls within the chain. Visualization plots. Chain execution timeline depicts the order and duration of chain steps. Model inference performance shows the distribution of inference times for different model calls. Fine-tune parameters. Logging level adjusts the verbosity of the logs. Enable visualization enables or disables visualization generation. Experiment name specifies the name of the Vertex AI experiment. Run names the specific run within the Vertex AI experiment. Model name identifies the Vertex AI model being used. Uncertainty methods. Probabilistic modeling if you are using models that provide confidence scores or probabilities. The callback can track these metrics. Ensemble methods if your chain incorporates multiple models. The callback can log the results and uncertainties from each model. Model uncertainty metrics. Vertex AI offers model uncertainty metrics, which can be logged and analyzed for better understanding of model predictions. Challenges and fixes. Challenge 1. Logging overhead. The callbacks logging operations can introduce performance overhead, especially in high-volume scenarios. Sample use case. If your chain processes a large volume of data, the logging overhead can significantly impact execution time. Fixes. Optimize logging level. Reduce the amount of logged data by setting a more selective logging level, e.g., info or warning instead of debug. Batch logging instead of logging each event individually. Batch events and log them in bulk for better performance. Asynchronous logging. Consider using asynchronous logging to avoid blocking the main chain. Execution thread. Challenge 2. Visualization complexity. Generating detailed visualizations for complex chains can be computationally expensive. Sample use case. If your chain involves multiple nested loops and conditional branches, creating comprehensive visualizations might be resource intensive. Fixes. Reduce visualization scope. Focus on visualizing key aspects of the chain, such as the overall flow, performance metrics, or specific areas of interest. Optimize visualization generation. Use efficient visualization libraries and techniques to minimize resource consumption. Use sampling if your chain processes a lot of data. Sample a representative subset for visualization to reduce complexity. Challenge 3. Integration with Vertex AI services. Connecting to Vertex AI resources and interacting with its services might require authentication and configuration. Sample use case. Authenticating to Vertex AI and configuring access to specific models or training resources might involve setting up service accounts or access tokens. Fixes. Proper authentication. Ensure that the code running your chain is properly authenticated with Vertex AI using service accounts or appropriate credentials. Configure API endpoints. Set the correct Vertex AI API endpoints in region settings. Utilize Vertex AI Python SDK. Leverage the Vertex AI Python SDK for seamless integration with its services. Langchain Google Vertex chains. Description: Langchain Google Vertex AI chains are specialized chains designed to seamlessly integrate Langchain's powerful capabilities with Google's Vertex AI platform. These chains leverage Vertex's advanced AI and milliliter services to enhance Langchain workflows, enabling users to perform complex tasks involving language understanding, generation, and reasoning, all powered by the cloud-based infrastructure and scalability of Vertex AI. Inputs. Input 1. Textual data. Langchain chains typically work with textual data as input, such as user queries, articles, documents, or conversational exchanges. This input data is processed and transformed by the chain's components. Input to Vertex AI model. The chain requires a Vertex AI model as input. This model can be a pre-trained model or a custom model trained on your specific data. The model defines the specific AI capabilities that the chain will utilize, such as text classification, question answering, or text generation. Outputs. Output 1 processed text. The chain outputs processed text based on the input data and pay. Capabilities of the Vertex AI model. This output can be a summarized version of the input, a generated response, or a classified category. Output 2 Vertex AI model predictions. The chain also returns the predictions generated by pay. Vertex AI model. This includes details like confidence scores, predicted classes, or generated text segments, providing insights into the model's reasoning process. Steps. Step 1 Data preparation. The input text is pre-processed and formatted to be compatible with the Vertex AI model's input requirements. This step might involve tokenization, embedding, or other data transformations. Step 2 Model invocation. The prepared data is sent to the Vertex AI model for processing. The model utilizes its trained knowledge to generate predictions or perform other tasks. Step 3 Output interpretation. The chain interprets the predictions received from the Vertex AI model and translates them into a format that is understandable and useful for the end user. This might involve generating human-readable text or summarizing the results. Metrics. Metric 1 Model accuracy measures the model's ability to correctly classify or predict the input data. This metric provides an indication of the model's performance on a specific task. Metric 2 Inference latency indicates the time taken by the Vertex AI model to process the input data and generate predictions. This metric reflects the efficiency of the model's execution. Visualization plots. Visualization plot 1 Model performance curve displays the model's accuracy or other relevant metrics across different input data points or parameters. This plot helps visualize the model's performance trends. Visualization plot 2 Prediction distribution visualizes the distribution of predictions generated by the model. This plot provides insights into the model's confidence levels and potential biases. Fine-tune parameters. Parameter 1 Learning rate determines the step size used during the training process of a custom Vertex AI model. This parameter affects the model's convergence rate and overall accuracy. Parameter 2 Batch size defines the number of samples processed during each training iteration. This parameter influences the training time and the model's generalization performance. Uncertainty methods. Uncertainty method 1 Monte Carlo dropout, a technique to estimate the uncertainty in model predictions by performing multiple forward passes with random dropout applied to the networks. Weights. This method provides a measure of the model's confidence in its predictions. Uncertainty method 2 Bayesian neural networks, a class of models that explicitly incorporate uncertainty into the model's parameters. This approach allows for more accurate estimation of uncertainty by considering the distribution of the model's parameters. Challenges and fixes. Challenge 1 Data compatibility issues. The input text format may not be directly compatible with the Vertex AI model's requirements. Sample use case that resulted in challenge 1 attempting to feed raw text into a model that expects pre-tokenized inputs. Fixes to challenge 1. Preprocess the text using appropriate techniques like tokenization, embedding, or formatting to match the model's expectations. Utilize pre-trained models that can handle raw text inputs. Use Langchain components designed for data preprocessing and transformation. Challenge 2. Model latency. High latency in the Vertex AI model can result in slow response times for the chain, impacting user experience. Sample use case that resulted in challenge 2 using a complex Vertex AI model that requires significant computational resources. Fixes to challenge 2. Optimize the model for speed, potentially using lightweight architectures or techniques like model quantization. Use Vertex is optimized inference services for faster processing. Utilize caching mechanisms to reduce redundant model calls. Challenge 3. Cold start issues. The first invocation of the Vertex AI model can be slow due to the need to load the model into memory. Sample use case that resulted in challenge 3 running the chain for the first time after deploying the Vertex AI model. Fixes to challenge 3. Utilize Vertex is managed models, which ensure that models are always ready for inference. Employ techniques like model preloading or warm-up routines to mitigate cold start delays. Use a load balancer to distribute incoming requests across multiple instances of the Vertex AI model. YAML. Langchain Google Vertex chains create structured runnable. Description: this chain is used to create a structured runnable, which is a Python function that can be executed on Google Vertex AI. The chain takes in a Langchain chain and converts it into a runnable Python function that can be deployed to Vertex AI. Inputs: chain a Langchain chain that will be converted into a runnable function. This chain can be any Langchain chain, including chains that use Google Vertex AI models. Projected: the Google Cloud project ID to which the runnable will be deployed. Region: the Google Cloud region to which the runnable will be deployed. Runtime: the Google Cloud runtime to use for the runnable. This runtime should include the necessary libraries for the Langchain chain to run. Outputs: runnable function, a Python function that can be executed on Google Vertex AI. This function will contain the logic of the Langchain chain. Steps: convert the Langchain chain into a Python function. Create a Google Vertex AI endpoint. Deploy the Python function to the Google Vertex AI endpoint. Metrics: execution time of the runnable function. Resource usage of the runnable function. Visualization plots: a plot of the execution time of the runnable function over time. A plot of the resource usage of the runnable function over time. Fine-tune parameters: the runtime environment for the runnable function. The resources allocated to the runnable function. Uncertainty methods: the chain can use uncertainty methods from the underlying Langchain chain. The chain can use uncertainty methods from the underlying Google Vertex AI models. Challenges and fixes. Challenge 1: the Langchain chain may not be compatible with Google Vertex AI. Sample use case that resulted in challenge 1: a Langchain chain that uses a library that is not supported on Google Vertex AI. Fixes to challenge 1: use a different Langchain chain, or modify the Langchain chain to use supported libraries. Challenge 2: the Google Vertex AI endpoint may not have enough resources for the Langchain chain to run. Sample use case that resulted in challenge 2: a Langchain chain that uses a large language model that requires a lot of resources. Fixes to challenge 2: increase the resources allocated to the Google Vertex AI endpoint. YAML. Langchain Google Vertex chains get output parser. Description: the get-output parser method is responsible for extracting and formatting the output of a Vertex AI model into a structured format suitable for further processing or analysis. This method is designed to work seamlessly with Langchain chains, enabling users to efficiently handle model responses and integrate them with other parts of their workflows. Inputs: model output: the raw output generated by the Vertex AI model, which can be in various formats depending on the model's nature, e.g. text, numerical values, structured data. Outputs: structured output: the method returns a structured representation of the model output, typically in a dictionary-like format, making it readily accessible and usable within Langchain chains. Steps: model response parsing: the method analyzes the raw model output and extracts relevant information based on the model's characteristics in the expected output format. This involves identifying specific fields, data types, and potential semantic relationships within the response. Data transformation: the extracted data is then transformed and organized into a structured output format. This might involve converting raw text to structured data, handling numerical values, and potentially performing other data manipulation steps to ensure consistency and usability. Metrics: output accuracy measures the correctness and relevance of the extracted information in relation to the original model output. This metric helps evaluate the effectiveness of the output parser in accurately representing the model's results. Parsing efficiency assesses the speed and computational cost of parsing the model output. This metric is important for optimizing the performance of the output parser, especially in real-time applications. Visualization plots: output structure visualization: a visual representation of the structured output format, highlighting the relationships between different elements and the overall organization of the data. This helps users understand the output structure and navigate its contents effectively. Data distribution plots: visualizations of the distribution of different data types within a structured output. This can reveal patterns, outliers, and potential biases in the model's output. Fine-tune parameters: output format customization allows users to tailor the structure and format of the output according to their specific requirements. This includes adjusting field names, data types, and the overall organization of the output. Model-specific parsing enables the output parser to adapt to the unique characteristics of different Vertex AI models, ensuring optimal extraction and formatting of model-specific outputs. Uncertainty methods: confidence scores: the output parser can include confidence scores associated with each element of the structured output. These scores represent the model's uncertainty in predicting specific values or categories, providing users with valuable insights into the reliability of the output. Model ensemble analysis: the parser can leverage multiple models for output generation and analyze the consistency and agreement between their outputs. This can help mitigate the uncertainty associated with individual models and improve the overall reliability of the results. Challenges and fixes. Challenge 1: handling complex model outputs. Some Vertex AI models may generate outputs with intricate structures, making it challenging to extract and format the information effectively. Sample use case that resulted in Challenge 1: a model that outputs a nested JSON structure with multiple levels of data and potentially varying field names. Fixes to Challenge 1: implementing flexible parsing mechanisms that can handle dynamic structures, and potentially using specialized libraries for JSON parsing to ensure accuracy and efficiency. Challenge 2. Dealing with model output errors. Vertex AI models might occasionally encounter errors or produce unexpected outputs, which could lead to parsing failures. Sample use case that resulted in challenge 2: a model that generates incomplete or corrupted data due to unforeseen conditions, resulting in errors during parsing. Fixes to challenge 2: implementing error handling mechanisms to identify and recover from common parsing errors. These could include robust exception handling, data validation checks, and fallback strategies to handle cases where the parsing process encounters unexpected conditions. Langchain Google Vertex chat models. Description: explain in detail. Langchain's Google Vertex AI chat models are a powerful tool for integrating large language models (LLMs) into your applications. They enable you to leverage the capabilities of Google's pre-trained models, like Palm 2, for tasks like text generation, summarization, translation, and more. Inputs. Input 1. Explain in detail. Prompt: this is the text you provide to the LLM. It's the core input that dictates the model's response. The prompt can be a question, a request for text generation, or instructions for a specific task. Input 2. Explain in detail. Context: you can provide additional context to the LLM, such as past conversations, relevant documents, or knowledge base information. This context helps the model better understand your request and generate more accurate and relevant responses. Outputs. Output 1. Explain in detail. Text response: the LLM generates text output based on your input and any provided context. This can be a formatted response, a generated story, a summarized document, or any other text-based output. Output 2. Explain in detail. Structured output optional depending on the model and your prompt. You might receive structured outputs like JSON objects, tables, or lists. This is particularly useful for tasks involving data extraction or organization. Steps. Step 1. Explain in detail. Initialization: you start by setting up your connection to Google Vertex AI and loading the desired LLM. This involves authenticating with Google Cloud and specifying the model you want to use. Step 2. Explain in detail. Prompt construction: craft your prompt carefully. It's crucial to provide clear and concise instructions for the LLM, especially when using context or complex prompts. Step 3. Explain in detail. Model interaction: send the prompt to the LLM. Vertex AI handles the model execution and returns the generated output. Step 4. Explain in detail. Output processing: handle the output from the LLM. This might involve formatting, extracting specific information, or integrating it into your application's logic. Metrics. Metric 1. Explain in detail. Accuracy for tasks like question answering or summarization. Evaluate the model's accuracy in providing correct and relevant information. Metric 2. Explain in detail. Fluency: measure how natural and coherent the generated text is, ensuring it reads like human written content. Metric 3. Explain in detail. Relevance: assess how well the generated output relates to the prompt and context, ensuring it addresses the desired topic. Visualization plots. Visualization plot 1. Explain in detail. Prompt response flowchart: visually represent the flow of information from prompt to response, highlighting the steps involved and the context used. Visualization plot 2. Explain in detail. Output analysis: use visualizations e.g. histograms, word clouds to analyze the characteristics of the generated text, such as word frequency, sentiment, or topic distribution. Fine-tune parameters. Parameter 1. Explain in detail. Temperature: control the randomness and creativity of the model's responses. A higher temperature leads to more unexpected and diverse outputs, while a lower temperature produces more predictable and conservative responses. Parameter 2. Explain in detail. Top K limits the number of possible outputs the model considers at each step of text generation. A lower value restricts the model to a smaller set of options, leading to more focused and predictable outputs. Parameter 3. Explain in detail. Top filters the possible outputs based on their probabilities. The model considers only outputs with probabilities above a certain threshold, resulting in more likely and coherent responses. Uncertainty methods. Uncertainty method 1. Explain in detail. Confidence scores. Some models provide confidence scores associated with their predictions. You can use these scores to identify areas where the model is less certain, indicating potential areas for further investigation or clarification. Uncertainty method 2. Explain in detail. Ensemble methods use multiple models or different configurations of the same model to generate multiple predictions. Analyze the agreement between these predictions to gauge the model's uncertainty. Challenges and fixes. Challenge 1. Explain in detail. Prompt engineering. Constructing effective prompts is crucial. A poorly worded prompt can lead to irrelevant or nonsensical outputs. Sample use case that resulted in challenge 1. You ask the model to write a story about a cat, but the output is a factual description of cats rather than a fictional narrative. Fixes to challenge 1. Provide specific instructions instead of just write a story. Specify the genre, length, and characters involved. For example, write a short fantasy story about a talking cat who saves a princess. Use clear and concise language. Avoid jargon or ambiguous terms. Test and iterate. Experiment with different prompts to find the best way to communicate your intentions to the model. Challenge 2. Explain in detail. Context handling. Managing context effectively is important for models that need to maintain conversational flow or work with large amounts of information. Sample use case that resulted in challenge 2. You ask the model a question about a specific topic, but it fails to incorporate relevant context from a previous conversation or a provided document. Fixes to challenge 2. Utilize context windows. Understand the limitations of the model's memory and provide context in a structured way. Employ techniques like summarization or keyword extraction. Condense large amounts of context into a more manageable form for the model to process. Challenge 3. Explain in detail. Model bias. LLMs can inherit biases from the training data, leading to potentially offensive or discriminatory outputs. Sample use case that resulted in challenge 3. The model generates a text that reinforces harmful stereotypes about certain groups. Fixes to challenge 3. Use models with built-in bias mitigation. Some models have been specifically trained to address bias. Monitor and evaluate outputs for bias regularly. Check model outputs for potential biases and implement mitigation strategies as needed. Promote diversity in training data. Ensure the training data used for the model represents a diverse range of perspectives and experiences. Challenge 4. Explain in detail. Cost optimization. Using Vertex AI models can incur costs, especially for frequent or resource-intensive tasks. Sample use case that resulted in challenge 4. The cost of running your application becomes unsustainable due to the frequent use of the LLM. Fixes to challenge 4. Optimize prompt construction. Reduce unnecessary words and avoid repetitive queries. Explore model selection. Consider using less expensive models for tasks that do not require full capabilities of the most powerful models. Utilize caching and other cost-saving strategies. Store and reuse previously generated outputs or results. Langchain Google Vertex Chat Models Chat Vertex AI. Description: the Chat Vertex AI class allows you to interact with a Google Vertex AI chat model, providing a user-friendly interface for text-based conversation with an AI model. Inputs: model name, the name of the Google Vertex AI chat model. It should be a valid Vertex AI model name. Endpoint: the endpoint URL of the Google Vertex AI model. This is the URL you use to access the model for prediction requests. Projected: optional, the Google Cloud project ID associated with your Vertex AI model. If not provided, the default project ID from your environment will be used. Location: optional, the Google Cloud region where the Vertex AI model is deployed. If not provided, the default location from your environment will be used. API key: optional, your Google Cloud API key. Use this if you don't want to set up service account authentication. Outputs: chat response, the text response generated by the Google Vertex AI chat model. Steps: initialize the Chat Vertex AI class with the required parameters: model name, endpoint, projected, location, API key. The class handles the communication with the Vertex AI model through its endpoint. When you call the run method with a user input, it sends a request to the Vertex AI model with the user's message. The model processes the message and generates a response, which is then returned by the run method. Metrics: latency, the time taken by the model to generate a response after receiving the user's message. Accuracy, the quality of the generated responses, measured by how relevant and informative they are to the user's input. Visualization plots: conversation history, a visualization of the conversation flow, showing the user's messages and the model's responses. Fine-tune parameters: none. Chat Vertex AI doesn't have fine-tuning parameters as it directly interacts with a pre-trained Google Vertex AI model. Uncertainty methods: none. Chat Vertex AI doesn't provide uncertainty methods, as it doesn't return probabilities or confidence scores for its predictions. Challenges and fixes: challenge 1, incorrect or invalid model name provided. Sample use case that resulted in challenge 1 providing a model name that doesn't exist in Vertex AI, or a misspelled name. Fixes to challenge 1: verify the model name in Vertex AI and ensure it's correctly spelled. Challenge 2: incorrect or invalid endpoint URL provided. Sample use case that resulted in challenge 2 providing an endpoint URL that doesn't point to a valid Vertex AI model or a URL with errors. Fixes to challenge 2: verify the endpoint URL in Vertex AI and ensure it's correct. Challenge 3: authentication issues. Sample use case that resulted in challenge 3: missing or invalid API key. Incorrect service account configuration. Fixes to challenge 3: ensure you have provided the correct API key or set up service account authentication correctly. Challenge 4: network issues. Sample use case that resulted in challenge 4: poor internet connectivity, network interruptions. Fixes to challenge 4: ensure you have a stable internet connection. Challenge 5: quota limits. Sample use case that resulted in challenge 5: exceeding the allowed number of requests to the Vertex AI model. Fixes to challenge 5: manage your requests by implementing rate limiting or batching to stay within the quota limits. Langchain Google Vertex embeddings. Description: explain in detail. The Langchain Google Vertex embeddings are a powerful tool that leverages Google Vertex AI to generate dense vector representations of text data. These embeddings can be used for a variety of downstream tasks, such as semantic search, text classification, and recommendation systems. Inputs: Input 1. Explain in detail text. The input to the embedding model is a string of text. This text can be a single sentence, a paragraph, or even a whole document. Input 2. Explain in detail model. The specific embedding model to use. Langchain provides several options, including text embedding ADA002, text embedding causal code, text embedding query distilbit base, and more. Each model has different strengths and weaknesses, and the choice of model will depend on the specific task. Outputs. Output 1. Explain in detail embedding. The output of the embedding model is a dense vector representation of the input text. The size of this vector will vary depending on the chosen model. Output 2. Explain in detail similarity score. When comparing two texts, a similarity score can be calculated based on the cosine similarity of their corresponding embeddings. Steps. Step 1. Explain in detail. The input text is preprocessed, which may involve tokenization, normalization, and stemming. Step 2. Explain in detail. The preprocessed text is fed into the chosen embedding model, which generates the dense vector representation. Metrics. Metric 1. Explain in detail. Cosine similarity measures the similarity between two vectors based on the angle between them. It ranges from -1 to 1, with 1 indicating perfect similarity and -1 indicating perfect dissimilarity. Metric 2. Explain in detail. Euclidean distance measures the distance between two vectors in Euclidean space. It is a good measure of similarity for small distances but less reliable for large distances. Visualization plots. Visualization plot 1. Explain in detail scatter plot. Visualize the relationship between different text embeddings in a 2D or 3D space. This can help to identify clusters of similar texts. Visualization plot 2. Explain in detail dimensionality reduction techniques such as principal component analysis PCA or T-SNE can be used to reduce the dimensionality of the embedding space and visualize it in a lower dimensional space. Fine-tune parameters. Parameter 1. Explain in detail model size. Different embedding models have varying numbers of parameters, which affects their accuracy and computational cost. Parameter 2. Explain in detail embedding dimensionality. The number of dimensions in the output embedding vector. Uncertainty methods. Uncertainty method 1. Explain in detail dropout, a technique that randomly drops out neurons during training, which helps to improve generalization and reduce overfitting. Uncertainty method 2. Explain in detail ensemble methods, combining multiple embedding models to generate an ensemble prediction, which can improve robustness and reduce uncertainty. Challenges and fixes. Challenge 1. Explain in detail limited context embedding models may struggle to capture the full context of long pieces of text. Sample use case that resulted in challenge 1. When embedding a large document, the model may not be able to capture the nuances of all the different sections. Fixes to challenge 1. Use a model with a larger context window. Break down the document into smaller chunks and embed each chunk separately. Challenge 2. Explain in detail computational cost. Generating embeddings can be computationally expensive, especially for large datasets. Sample use case that resulted in challenge 2. When embedding a large number of documents, the processing time can be significant. Fixes to challenge 2. Use a smaller embedding model. Use a cloud-based platform with dedicated GPUs or TPUs. Consider using an approximate nearest neighbor search and algorithm to speed up similarity searches. Langchain Google Vertex embeddings. Google embedding model type. Description: the Google embedding model type is a Langchain integration for utilizing Google Vertex is embedding models to generate vector representations of text. It leverages the power of pre-trained models from Google to embed text into a multidimensional space, enabling tasks like semantic similarity search, clustering, and text classification. Inputs. Text: the input text that will be converted into a vector representation. It can be a single sentence, a paragraph, or a longer document. Outputs. Embedding: the output is a numerical vector representation of the input text. The length of the vector depends on the specific embedding model chosen. This vector captures the semantic meaning of the text. Steps. Model selection: choose a pre-trained embedding model from Google Vertex is model catalog based on your specific requirements and the desired semantic representation. Embedding generation: pass the input text to the selected model, which will generate the corresponding embedding vector. Metrics. Similarity: calculate cosine similarity between different embedding vectors to measure the semantic relatedness between the corresponding texts. Visualization plots. Embedding projection: visualize the embedding vectors in a lower dimensional space, typically 2D or 3D, to gain insights into the relationships between different texts. Fine-tune parameters. Non-Google Vertex is embedding models are pre-trained and generally do not support fine-tuning. Uncertainty methods. Non-Google Vertex is embedding models do not provide uncertainty estimates or confidence scores for the generated embeddings. Challenges and fixes. Challenge 1: choosing the right embedding model. Sample use case that resulted in challenge 1: choosing an embedding model that is not optimized for the specific domain or task can lead to suboptimal performance. Fixes to challenge 1: consult Google Vertex is model catalog to select an embedding model tailored to your specific needs, such as text classification, semantic search, or question answering. Consider experimenting with different models to find the best fit for your application. Challenge 2: handling large input texts. Sample use case that resulted in challenge 2: processing long documents or large amounts of text can be computationally expensive and time-consuming. Fixes to challenge 2: explore techniques like sentence-level embedding or chunking the text into smaller segments to handle large inputs more efficiently. Langchain Google Vertex embeddings. Vertex AI embeddings. Description: explain in detail. Vertex AI embeddings is a Langchain embedding class that utilizes Google Vertex is embedding API for generating vector representations of text. It allows you to leverage the power of Vertex is pre-trained embedding models for tasks such as semantic search, text clustering, and recommendation systems. Inputs. Input 1: explain in detail texts. A list of strings representing the text inputs to be embedded. Each string in the list will be independently embedded. Input 2: explain in detail model name. The name of the Vertex AI embedding model to use. You can choose from a variety of pre-trained models offered by Google Vertex AI. Outputs. Output 1: explain in detail a list of embedding vectors, where each vector corresponds to an input text in the texts list. The embedding vectors are multidimensional arrays representing the semantic meaning of the input text. Output 2: explain in detail a dictionary containing additional metadata about the embedding process, such as the model used in the embedding dimension. Steps. Step 1: explain in detail the input text is preprocessed, e.g. tokenization, normalization to prepare it for embedding. Step 2: explain in detail the preprocessed text is passed to the specified Vertex AI embedding model, which generates the embedding vector representation. Metrics. Metric 1. Explain in detail similarity metrics, e.g. cosine similarity. Euclidean distance can be used to evaluate how well the embedding vectors capture the semantic relationships between the input texts. Metric 2. Explain in detail model performance can be assessed based on downstream tasks, such as the accuracy of semantic search or the quality of text clustering results. Visualization plots. Visualization plot 1. Explain in detail embeddings can be visualized in low-dimensional space using techniques like tsna or PCA, allowing for insights into the relationships between texts. Visualization plot 2. Explain in detail. You can visualize the similarity between documents based on their embedding vectors, creating heat maps or dendrograms to understand clusters and relationships. Fine-tune parameters. Parameter 1. Explain in detail model name. You can choose from a variety of pre-trained models offered by Google Vertex AI, allowing you to select the most suitable model for your specific use case. Parameter 2. Explain in detail endpoint. If you have a custom Vertex AI embedding model deployed as an endpoint, you can specify the endpoint address to use that model instead of the pre-trained ones. Uncertainty methods. Uncertainty method 1. Explain in detail. Currently, Vertex AI embeddings doesn't offer built-in uncertainty estimation. However, you can potentially use techniques like ensemble methods or Bayesian neural networks to estimate uncertainty in the embeddings. Uncertainty method 2. Explain in detail. If you are using a custom Vertex AI embedding model, you can incorporate uncertainty estimation methods into the model's architecture during training. Challenges and fixes. Challenge 1. Explain in detail model selection. Choosing the right Vertex AI embedding model for your specific task can be challenging. Different models have varying strengths and weaknesses in capturing semantic nuances. Sample use case that resulted in challenge 1. You might choose a model that excels in capturing syntactic similarity but performs poorly for semantic similarity, leading to inaccurate results. Fixes to challenge 1. Experiment with different pre-trained models and evaluate their performance on your specific task using benchmark datasets or downstream metrics. Challenge 2. Explain in detail resource consumption. Embedding large volumes of text can consume significant computational resources, especially when using complex models. Sample use case that resulted in challenge 2. You might encounter slow response times or even timeouts when embedding a large dataset. Fixes to challenge 2. Consider using optimized embedding models, reducing the input text size, or leveraging batch processing techniques to mitigate resource consumption issues. Langchain Google Vertex functions utils. Description: the functions utils module within Langchain's Google Vertex AI integration provides a set of utilities for working with Vertex's functions. These functions streamline the interaction between Langchain and Vertex AI, simplifying tasks like deploying models and interacting with them. Inputs. Function definition: the module requires a function definition to be provided. This function represents the core logic you want to execute within Vertex AI. The function should be written in a supported language, e.g. Python, and adhere to Vertex's function deployment requirements. Vertex AI endpoint configuration: to deploy and interact with functions, you'll need to configure the Vertex AI endpoint where your function will reside. This includes specifying the region, endpoint name, and other relevant settings. Outputs. Deployed function: the functions utils module helps you deploy the provided function to the Specified Vertex AI endpoint. This results in a deployed function ready to be invoked. Function invocation results after deployment. You can use the module's utilities to invoke the deployed function. The module facilitates this invocation process, returning the results of the executed function. Steps. Function packaging. The module assists in packaging your function definition into a format suitable for deployment to Vertex AI. Endpoint configuration. You need to provide the configuration details for the Vertex AI endpoint, where the function will be deployed. Deployment. The module handles the deployment process, uploading the packaged function to the specified Vertex AI endpoint. Function invocation. The module provides methods to easily invoke the deployed function, sending input data and receiving the function's output. Metrics. Function execution time. The module can track the execution time of your function to analyze its performance. Function invocation count. You can monitor the number of times the deployed function is invoked to understand usage patterns. Visualization plots. Function invocation timeline. Visualizing the timing of function invocations can help identify patterns and potential bottlenecks. Function execution time distribution. A distribution plot of execution times can reveal variations in performance and highlight potential areas for optimization. Fine-tune parameters. Vertex AI function configuration. You can fine-tune the configuration of your Vertex AI function, adjusting parameters like memory allocation and resource requests to optimize performance. Uncertainty methods. Not directly applicable. Uncertainty quantification is typically associated with machine learning models. Vertex AI functions are designed for executing code, not for making probabilistic predictions. So uncertainty methods are not directly applicable. Challenges and fixes. Challenge 1. Deployment errors. Deployment issues can arise if the function definition doesn't meet Vertex IS requirements or if the endpoint configuration is incorrect. Sample use case that resulted in challenge 1. Attempting to deploy a function with an unsupported language or a function that exceeds the resource limits for the specified endpoint. Fixes to challenge 1. Verify function compatibility. Ensure your function is written in a supported language and that it adheres to Vertex IS function specifications. Check endpoint configuration. Carefully review the endpoint configuration, ensuring it aligns with your function's requirements and available resources. Challenge 2. Function invocation issues. Problems with invoking the deployed function can occur due to incorrect input data formats, network connectivity issues, or limitations within the Vertex AI environment. Sample use case that resulted in challenge 2. Providing invalid input data to the function or experiencing network connectivity problems during invocation. Fixes to challenge 2. Validate input data. Check the data format before sending it to the deployed function to ensure compatibility. Verify network connectivity. Confirm that your system has a stable connection to the Vertex AI endpoint. Review function logs. Examine the logs generated by Vertex AI for error messages or other information that can help pinpoint the cause of invocation issues. Langchain Google Vertex functions utils parameters schema. Description. The parameters schema class defines the input and output parameters for a function. It is used by the function's utils class to create and validate function calls. Inputs. Function name. The name of the function to be called. Function arguments. A dictionary of arguments to be passed to the function. Outputs. Function output. The output of the function. Steps. Create a parameters schema object. Set the input and output parameters for the function. Use the function's utils class to create and validate function calls. Metrics. Function execution time, the time taken to execute the function. Visualization plots. Function call graph, a visual representation of the function call hierarchy. Fine-tune parameters. None. Uncertainty methods. None. Challenges and fixes. Challenge 1, the function name may not be valid. Sample use case that resulted in challenge 1 using an invalid function name, such as my function. Fixes to challenge 1 ensure that the function name is valid and exists. Challenge 2, the function arguments may not be valid. Sample use case that resulted in challenge 2 using an invalid argument type or value, such as passing a string to a function that expects an integer. Fixes to challenge 2 ensure that the function arguments are valid and of the correct type. Challenge 3, the function may not be accessible. Sample use case that resulted in challenge 3 using a function that is not in the current scope, such as a function defined in another module. Fixes to challenge 3 ensure that the function is accessible in the current scope. Challenge 4, the function may raise an exception. Sample use case that resulted in challenge 4 using a function that throws an exception, such as a function that divides by 0. Fixes to challenge 4 handle exceptions appropriately and gracefully. YAML. Langchain Google Vertex functions utils pedantic functions output parser. Description: the pedantic functions output parser class is a specialized parser designed to handle output from functions that return data structured according to pedantic models. Pedantic is a Python library for data validation and parsing, known for its powerful data typing features. This parser ensures that the output from the functions is formatted and validated correctly, making it suitable for seamless integration within Langchain pipelines. Inputs. Function output. This input represents the raw output returned by the function. It is expected to be a pedantic model instance, containing data organized according to the model's schema. Outputs. Parsed output. This output is the result of parsing the function's output. It will be a dictionary containing the data extracted from the pedantic model. The keys of this dictionary correspond to the fields defined in the model, and the values are the actual data values. Steps. Model instantiation. The parser first initializes an instance of the pedantic model class. This instance serves as a template to guide the validation and parsing process. Data extraction. The parser then extracts the data from the function's output. It iterates over the fields of the pedantic model and extracts the corresponding values from the function output. Validation. Pedantic's built-in validation mechanisms are used to ensure that the extracted data conforms to the data types and constraints defined in the model schema. If any data violates the model's schema, the parser will raise an exception, signaling an issue with the function's output. Challenges and fixes. Challenge 1. Function output is invalid. Sample use case that resulted in challenge 1. The function might return data that does not match the expected structure defined by the pedantic model. For example, a field might be missing, or a value might be of the wrong data type. Fixes to challenge 1. Validate function output. Implement robust validation checks within the function itself to ensure it always returns data compliant with the pedantic model schema. Add error handling. Incorporate error handling within the parser to catch and manage potential validation errors, providing helpful messages to guide troubleshooting. Challenge 2. Pedantic model is missing. Sample use case that resulted in challenge 2. The parser might be used with a function that does not Return a pedantic model instance, leading to unpredictable behavior. Fixes to challenge 2. Model dependency. Ensure that the function clearly documents its expected output, including the specific pedantic model it will return. Parameter validation. Validate the function's input parameters to ensure that the necessary pedantic model is supplied. Langchain Google Vertex Gemma. Description. Explain in detail. The Langchain Google Vertex Gemma is a powerful tool that combines the capabilities of Langchain and Google Vertex AI. It allows you to build and deploy sophisticated AI applications that leverage the strengths of both frameworks. Langchain provides the ability to chain together different AI components, such as language models, text embeddings, and retrieval systems, while Google Vertex AI offers a managed platform for training, deploying, and managing machine learning models. Inputs. Input 1. Explain in detail text or data. The Gemma can take various input formats, including raw text, structured data, or even pre-processed embeddings. This input will be the basis for the AI tasks you want to perform. Input 2. Explain in detail Vertex AI model. You can provide a pre-trained Vertex AI model, such as a language model, a classification model, or a recommender system. This model will be used for processing the input data and generating outputs. Outputs. Output 1. Explain in detail textual outputs. The Gemma can generate different types of textual outputs, including summarized text extracting key insights or summaries from your input, translated text translating text into different languages, generated text creating new content based on prompts or input data, chatbot responses engaging in interactive conversations with users. Output 2. Explain in detail structured outputs. You can get structured outputs like classifications, predictions, or recommendations. Steps. Step 1. Explain in detail input pre-processing. The Gemma might pre-process your input data, such as cleaning it, tokenizing it, or converting it into embeddings. Step 2. Explain in detail model interaction. The pre-processed input is then fed into the specified Vertex AI model. Step 3. Explain in detail output post-processing. The model outputs are processed and formatted into a human-readable or machine-processable output. Metrics. Metric 1. Explain in detail accuracy for classification tasks. The accuracy measures how often the model correctly predicts the class of the input. Metric 2. Explain in detail precision and recall. These metrics are relevant for tasks like information retrieval, where you want to evaluate the model's ability to identify relevant information and avoid irrelevant results. Visualization plots. Visualization plot 1. Explain in detail confusion matrix. This plot visually represents the performance of a classification model, showing how well it predicts different classes. Visualization plot 2. Explain in detail precision recall curve. This plot helps assess the trade-off between precision and recall for different classification thresholds. Fine-tune parameters. Parameter 1. Explain in detail learning rate controls how quickly the model adjusts its parameters during training. Parameter 2. Explain in detail batch size defines the number of training examples used in each training iteration. Parameter 3. Explain in detail epochs represents the number of times the model iterates over the entire training dataset. Uncertainty methods. Uncertainty method 1. Explain in detail confidence scores. The model can provide confidence scores for its predictions, indicating the level of certainty it has about its outputs. Uncertainty method. To explain in detail ensemble methods combining multiple models to reduce uncertainty and improve robustness. Challenges and fixes. Challenge 1. Explain in detail model selection. Choosing the right Vertex AI model for your specific task can be challenging. Sample use case that resulted in challenge 1. You might want to translate text, but you need to select a model that is specifically designed for translation. Fixes to challenge 1. Carefully consider the type of task you want to perform and choose a model that is best suited for it. Explore available models on the Vertex AI platform and consult documentation to understand their strengths and weaknesses. Challenge 2. Explain in detail data preparation. Preparing data for training or input to Vertex AI models often requires significant effort. Sample use case that resulted in challenge 2. You might need to clean your text data, remove irrelevant information, or format it in a way that the model can understand. Fixes to challenge 2. Use data pre-processing techniques to ensure your data is clean and consistent. Leverage tools and libraries within Vertex AI or external libraries to help you with data transformation and cleaning. Challenge 3. Explain in detail model deployment. Deploying and managing your trained model in production requires specific infrastructure and processes. Sample use case that resulted in challenge 3. You might need to scale your model to handle a large volume of requests or ensure high availability and performance. Fixes to challenge 3. Leverage Vertex's managed deployment features, which take care of infrastructure and scaling. Follow best practices for model deployment and monitoring to ensure smooth operation. Challenge 4. Explain in detail cost optimization. Training and deploying AI models can be expensive. Sample use case that resulted in challenge 4. You might need to reduce the training time or pay number of compute resources required for model deployment. Fixes to challenge 4. Explore options for cost optimization within Vertex AI, such as using pre-trained models, optimizing hyperparameters, and selecting the right compute resources. YAML. Langchain Google Vertex Gemma Chat Local HF. Description: Gemma Chat Local HF is a Gemma chatbot built using a local Hugging Face transformer model. It allows you to use Google Vertex AI to manage and run the chatbot, while utilizing the flexibility of a local Hugging Face model for customization and fine-tuning. Inputs. Prompt the user's input query or question. Model a Hugging Face transformer model downloaded locally, e.g., a pre-trained model or a fine-tuned version. Outputs. Chatbot response: the generated response from the model based on the user's input. Conversation history: a record of the past interactions with the chatbot, including user prompts and model responses. Steps. User sends a prompt to the Gemma Chat Local HF chatbot. The prompt is processed and sent to the local Hugging Face transformer model. The model generates a response based on its training data and the input prompt. The response is returned to the user through the Gemma interface. The conversation history is updated with the new prompt and response. Metrics. Accuracy measured as the percentage of accurate responses generated by the chatbot. Fluency evaluates the naturalness and coherence of the chatbot's responses. User satisfaction determined through user feedback and engagement with the chatbot. Visualization plots. Conversation history plot visualizes the flow of interactions between the user and the chatbot. Model accuracy trends tracks the accuracy of the model over time, potentially after updates or fine-tuning. Fine-tune parameters. Learning rate controls the step size during model optimization. Number of epochs: the number of passes through the training data during fine-tuning. Batch size, the number of samples processed together during each training step. Uncertainty methods. Temperature scaling adjusts the randomness of the model's responses to control the level of uncertainty. Top K sampling selects the top K most likely tokens for generation, reducing the probability of unlikely responses. Challenges and fixes. Challenge 1. Limited context. The model may struggle to remember previous interactions in long conversations. Sample use case that resulted in challenge 1. A user asking for a product recommendation, then asking about a different product without reminding the bot of the previous request. Fixes to challenge 1. Implement a conversation history mechanism to store previous prompts and responses. Use a larger context window in the model configuration to allow for a longer memory. Challenge 2. Model bias. The model might reflect biases present in the training data. Sample use case that resulted in challenge 2. The model generates offensive or discriminatory responses when asked about sensitive topics. Fixes to challenge 2. Train the model on a diverse and unbiased dataset. Implement bias mitigation techniques during model training. Use a fairness evaluation metric to assess bias in the model's outputs. Challenge 3. Overfitting. The model might memorize the training data too well and struggle to generalize to unseen prompts. Sample use case that resulted in challenge 3. The model performs well on training data but struggles with new, unseen inputs. Fixes to challenge 3. Use regularization techniques during model training to prevent overfitting. Implement early stopping to avoid overfitting on the training data. Split the data into training, validation, and test sets to assess generalization performance. Langchain Google Vertex Gemma Chat Local Kaggle. Description: This tool leverages Langchain and Google Vertex AI to construct the chatbot that interacts with the local Kaggle dataset. It employs Gemma for generating text responses based on data insights extracted from the dataset. Inputs: Kaggle dataset path. The local path to the Kaggle dataset to be used is the chatbot's knowledge base. User query: the user's question or prompt that the chatbot needs to respond to. Outputs: Chatbot responds the text generated by Gemma, providing insights from the Kaggle dataset relevant to the user's query. Steps: Data loading. The Kaggle dataset is loaded into memory using Langchain's data loading capabilities. Data understanding. The dataset structure, schema, and key insights are analyzed to identify relevant information for chatbot interaction. Query processing. The user's query is processed and transformed into a format suitable for querying the dataset. Data retrieval based on the processed query. Relevant data points are retrieved from the Kaggle dataset. Gemma interaction. The retrieved data is provided to Gemma, which generates a textual response summarizing the insights and information found within a dataset. Response formatting. The Gemma-generated response is formatted appropriately for the chatbot interface, ensuring clarity and readability. Metrics: Accuracy assesses the correctness of the chatbot's responses against ground truth information from the Kaggle dataset. Relevance measures the degree to which the chatbot's responses address the user's intended query and provide relevant information. Fluency evaluates the coherence, grammar, and readability of the chatbot's generated text. Visualization plots. Data distribution plots visualize the distribution of data points within the Kaggle dataset, providing insights into key characteristics and trends. Correlation plots show relationships between different variables in the dataset, revealing potential patterns and dependencies. Fine-tune parameters. Gemma model parameters fine-tune Gemma's model parameters to optimize its ability to generate text responses that are tailored to the specific Kaggle dataset and user queries. Uncertainty methods. Confidence scores provide estimations of the chatbot's confidence in its generated responses, indicating areas where the information might be less certain. Challenges and fixes. Challenge 1: Data complexity. Handling datasets with complex schemas and large amounts of data can pose challenges for data retrieval and processing. Sample use case that resulted in Challenge 1: A dataset containing millions of rows and hundreds of columns can lead to long processing times and potential memory issues. Fixes to Challenge 1: Data sampling. Employ techniques like random sampling or stratified sampling to reduce the data size while maintaining representative information. Data indexing. Utilize data indexing methods, e.g., Elasticsearch, to efficiently retrieve relevant data points based on user queries. Challenge 2: Ambiguous queries. Users may express their queries in a way that is unclear or open to multiple interpretations, leading to incorrect or irrelevant responses. Sample use case that resulted in Challenge 2: A query like "What is the average price?" could be ambiguous without context on which product or category the user is referring to. Fixes to Challenge 2: Query clarification. Employ techniques like context-aware language models or interactive query refinement to ensure the user's intent is understood correctly. Query expansion. Use techniques like keyword extraction and related term identification to expand the query and capture the user's intent more broadly. Langchain. Google Vertex Gemma Chat Vertex AI Model Garden. Description. Explain in detail. This Gemma model is a large language model (LLM) specifically designed for conversational interactions. It leverages Google Vertex AI to access and utilize the powerful capabilities of pre-trained LLM models, allowing for advanced natural language understanding and generation. Inputs. Input 1: Explain in detail. Textual input in the form of a natural language query or prompt. This can include questions, instructions, or conversational messages. Input 2: Explain in detail. Optional context or background information that can be provided to the model to help it understand the query better. This could be previous conversations, relevant documents, or any other contextual information. Outputs. Output 1: Explain in detail. Textual response generated by the model in natural language, providing answers, summaries, creative outputs, or other desired results based on the input. Output 2: Explain in detail metadata about the generated response, such as confidence scores, model details, or other relevant information. Steps. Step 1: Explain in detail. The input text is preprocessed and tokenized, transforming it into a format suitable for the LLM. Step 2: Explain in detail. The preprocessed input is fed into the LLM, which processes the text and generates a response based on its training data and the provided context. Step 3: Explain in detail. The generated response is post-processed and formatted to be human-readable and presented to the user. Metrics. Metric 1: Explain in detail. Perplexity, a measure of how well the model predicts the next word in a sequence. Lower perplexity indicating better performance. Metric 2: Explain in detail. Blue score, a measure of the quality of machine translation, assessing how closely the generated text matches a reference translation. Visualization plots. Visualization plot 1: Explain in detail. Attention visualizations, showing which parts of the input text the model focused on when generating the response. Visualization plot 2: Explain in detail. Word embedding visualizations, displaying the semantic Relationships between words in the input and output text. Fine-tune parameters. Parameter 1. Explain in detail learning rate, the rate at which the model's weights are adjusted during training, influencing the speed and accuracy of the learning process. Parameter 2. Explain in detail batch size, the number of samples processed at a time during training, affecting the computational efficiency and training stability. Uncertainty methods. Uncertainty method 1. Explain in detail temperature scaling, adjusting the model's output distribution to control its confidence and avoid overly certain responses. Uncertainty method 2. Explain in detail Monte Carlo dropout, introducing randomness during inference to estimate the model's uncertainty and provide a range of possible outputs. Challenges and fixes. Challenge 1. Explain in detail bias in the model's outputs. The model may generate responses that reflect biases present in its training data. Sample use case that resulted in challenge 1. A query asking for a doctor may result in the model primarily suggesting male doctors, reflecting gender biases in the training data. Fixes to challenge 1. Use debiasing techniques during training to mitigate biases in the model's outputs. Implement fairness evaluation metrics to assess and monitor the model's fairness across different demographics. Provide diverse and representative training data to reduce biases. Challenge 2. Explain in detail lack of context awareness. The model may fail to understand the context of a conversation and provide irrelevant or incoherent responses. Sample use case that resulted in challenge 2. A query asking for a restaurant recommendation without specifying the location might result in the model recommending restaurants from a different city or region. Fixes to challenge 2. Incorporate contextual information into the input, such as previous conversation history or user location. Train the model on a more diverse range of conversational contexts to improve its ability to understand and respond appropriately. Implement techniques like memory networks to allow the model to retain and utilize past information. Challenge 3. Explain in detail limited knowledge base. The model may lack information about specific topics or events. Sample use case that resulted in challenge 3. A query asking about a recent news event might result in the model providing outdated or inaccurate information. Fixes to challenge 3. Train the model on a wider range of data, including up-to-date information sources. Provide access to external knowledge bases or APIs to retrieve and integrate current information. Implement methods for continual learning to update the model with new information over time. Langchain Google Vertex Gemma Local HF. Description: Gemma Local HF is a Langchain integration with Google Vertex is Gemma, a framework for building and deploying machine learning models for text data. It provides an efficient way to utilize Gemma's capabilities for text classification, text generation, and other NLP tasks within the Langchain framework. Inputs. Input 1. Text data. Gemma Local HF accepts text data as input. This data can be in the form of strings, lists of strings, or any format compatible with Langchain's text processing capabilities. Input 2. Gemma model path. The path to the saved Gemma model. This model should be a pre-trained or fine-tuned model compatible with the desired task. Outputs. Output 1. Predictions. The model's predictions based on the input text data. These predictions can be in various forms depending on the task, e.g. class labels for classification, generated text for text generation. Output 2. Confidence scores, optional if available. The model's confidence scores for each prediction. This provides insights into the model's certainty about its predictions. Steps. Step 1. Load Gemma model. The Gemma local HF tool first loads the specified Gemma model from the provided path. Step 2. Pre-process text. The input text data is pre-processed according to the requirements of the Gemma model. This may include tasks like tokenization, stemming, or lemmatization. Step 3. Make predictions. The pre-processed text is fed to the loaded Gemma model for making predictions. Step 4. Post-process results. The model's predictions are then post-processed and returned in a format suitable for Langchain's further processing. Metrics. Metric 1. Accuracy. For classification tasks, accuracy measures the percentage of correctly classified instances. Metric 2. F1 score. A harmonic mean of precision and recall, providing a balanced measure for tasks where both false positives and false negatives are important. Metric 3. Blue score. For text generation tasks, Blue score measures the similarity between the generated text and reference human written text. Visualization plots. Visualization plot 1. Confusion matrix. For classification tasks, a confusion matrix visually displays the model's performance, showing correct and incorrect predictions for each class. Visualization plot 2. Precision recall curve. For classification tasks, a precision recall curve helps visualize the trade-off between precision and recall at different threshold values. Visualization plot 3. Attention heat maps. For text generation tasks, attention heat maps can be used to visualize the model's attention mechanism, highlighting which words in the input text influence the generation of specific output words. Fine-tune parameters. Parameter 1. Learning rate. Controls the step size taken during model optimization. Parameter 2. Number of epochs. The number of times the training data is iterated over during model training. Parameter 3. Batch size. The number of samples used in each iteration of model training. Uncertainty methods. Uncertainty method 1. Monte Carlo dropout. This method uses multiple forward passes with random dropout masks to estimate prediction uncertainty. Uncertainty method 2. Ensemble of models. Training multiple models with slightly different parameters and combining their predictions can provide a measure of uncertainty. Challenges and fixes. Challenge 1. Model performance degradation. The model's performance might decline when deployed to a new environment or with new data. Sample use case that resulted in challenge 1. A model trained on a dataset of news articles might perform poorly on a dataset of customer reviews due to different writing styles and language patterns. Fixes to challenge 1. Fine-tuning the model with a dataset that is representative of the target deployment environment or data distribution. Using data augmentation techniques to create synthetic data that is similar to the target data. Distribution. Employing techniques like transfer learning, where a pre-trained model is adapted to the new task. Challenge 2. Limited model explainability. It can be challenging to understand why the model makes specific predictions, which can hinder trust in the model's output. Sample use case that resulted in challenge 2. A model predicts a customer review as negative, but it's unclear from the model's output which words in the review led to that prediction. Fixes to challenge 2. Using techniques like attention mechanisms or gradient-based feature attribution to gain insights into the model's decision-making process. Generating explanations for model predictions using tools like Lime Local Interpretable Model Agnostic Explanations. Employing visualization techniques to understand model behavior, such as attention heat maps or feature importance plots. Challenge 3. Resource constraints. Deploying a large Gemma model might require significant computational resources, making it expensive or challenging for certain applications. Sample use case that resulted in Challenge 3: a company with limited cloud infrastructure resources wants to deploy a large language model for customer interaction but faces constraints in terms of processing power and memory. Fixes to Challenge 3: exploring smaller or more efficient GEMMA models that are suited for the specific task. Leveraging techniques like model compression or quantization to reduce model size and memory footprint. Utilizing cloud-based platforms with scalable infrastructure for model deployment and execution. Challenge 4: data leakage. If the model is trained on data that contains sensitive information, it might leak this information during predictions. Sample use case that resulted in Challenge 4: a model trained on a data set of medical records might inadvertently reveal patient-specific details in its predictions. Fixes to Challenge 4: implementing data anonymization techniques to remove sensitive information before training a model. Employing differential privacy techniques to protect individual data while training the model. Applying data masking or redaction techniques to hide sensitive information from the model's input. Langchain Google Vertex GEMMA Local Kaggle. Description: this tool utilizes the Langchain library, Google Vertex AI, and the GEMMA Local Kaggle dataset to facilitate building and deploying powerful language models. GEMMA Local Kaggle provides a curated collection of Kaggle datasets, enabling users to train and fine-tune models on diverse real-world data. Vertex AI serves as a robust platform for model training, deployment, and monitoring. Inputs: GEMMA Local Kaggle dataset, a curated collection of Kaggle datasets specifically designed for language model training and evaluation. These datasets can range from text-based datasets like news articles or social media posts to datasets with structured information, like product reviews or scientific research papers. User-defined prompt: a text prompt that specifies the desired task or question for the language model to process. This prompt could be a question to be answered, a request for text summarization, or a creative writing prompt. Outputs: model predictions, the language model's responses to the user-defined prompts, generated based on the training data from the GEMMA Local Kaggle dataset. Model performance metrics: evaluation metrics that assess the model's accuracy, effectiveness, and efficiency on the GEMMA Local Kaggle dataset. This could include metrics like perplexity, accuracy, or recall, depending on the task. Steps: data loading and preprocessing: the GEMMA Local Kaggle dataset is loaded into the system and preprocessed to prepare it for training the language model. This includes tasks like cleaning the data, removing noise, and converting text to numerical representations. Model training: the preprocessed GEMMA Local Kaggle data is used to train a language model using Vertex's powerful training infrastructure. This involves defining the model architecture, selecting a suitable training algorithm, and setting hyperparameters for optimal performance. Model evaluation: once trained, the language model is evaluated on the GEMMA Local Kaggle dataset to assess its performance. This involves comparing the model's predictions against ground truth labels and calculating relevant performance metrics. Model deployment and inference: the trained language model is deployed on Vertex AI, making it available for inference. Users can then interact with the model by submitting their prompts, receiving responses based on the learned patterns from the GEMMA Local Kaggle dataset. Metrics: accuracy: a measure of how well the model's predictions match the ground truth labels in the GEMMA Local Kaggle dataset. Perplexity: a metric that measures the model's ability to predict the next word in a sequence. providing insight into the model's fluency and coherence. Recall a measure of the model's ability to correctly identify positive instances in the dataset. Particularly relevant for tasks like sentiment analysis or entity extraction. Visualization plots. Model accuracy over epochs. A plot that illustrates the model's accuracy on the GEMA local Kaggle dataset throughout the training process, providing insights into convergence and learning progress. Confusion matrix. A visualization that displays the model's performance across different classes, highlighting potential misclassifications and areas for improvement. Fine-tune parameters. Learning rate determines the step size for adjusting the model's weights during training, influencing the speed and stability of learning. Batch size. The number of data samples processed in a single iteration during training, affecting the model's performance and training time. Uncertainty methods. Monte Carlo dropout. A method that introduces randomness during inference, allowing the model to estimate its confidence in its predictions and quantify uncertainty. Bayesian neural networks. Models that incorporate prior beliefs about the model parameters, enabling them to express uncertainty in their predictions based on the training data. Challenges and fixes. Challenge 1. Overfitting. The model may perform well on the GEMA local Kaggle training data but generalize poorly to unseen data. Sample use case that resulted in Challenge 1. Training a language model on a small GEMA local Kaggle dataset with highly specific keywords, resulting in the model memorizing the dataset and failing to recognize new examples with slightly different wording. Fixes to Challenge 1. Regularization techniques like L1 or L2 regularization, early stopping, or using a larger, more diverse GEMA local Kaggle dataset to enhance the model's generalization ability. Challenge 2. Data imbalance. The GEMA local Kaggle dataset might exhibit class imbalance, where some classes are represented significantly more than others, leading to biased model predictions. Sample use case that resulted in Challenge 2. Training a sentiment analysis model on a GEMA local Kaggle dataset with a large number of positive reviews and a small number of negative reviews, causing the model to primarily predict positive sentiment even for negative examples. Fixes to Challenge 2. Techniques like oversampling minority classes, undersampling majority classes, or using weighted loss functions during training to mitigate the imbalance and improve the model's performance on underrepresented classes. Langchain Google Vertex GEMA Vertex AI Model Garden. Description: The GEMA Vertex AI Model Garden is a Langchain tool that enables the use of Google Vertex is pre-trained models within Langchain chains. It leverages Google Vertex is Model Garden, a collection of pre-trained models for various tasks like text generation, summarization, and classification. This tool facilitates the seamless integration of these powerful models into Langchain workflows, allowing for advanced capabilities within conversational AI applications. Inputs: model name, the name of the pre-trained model from Vertex AI Model Garden. This name should be a valid model identifier within Vertex AI. For example, Text DaVinci 003 for a text generation model. Projected: the Google Cloud Project ID where the Vertex AI Model Garden model is hosted. This is required for authorization and model access. Location: the region of the Vertex AI Model Garden model. For instance, US Central 1. Outputs: response, the output of the selected Vertex AI Model Garden model, tailored to the specific task defined by the model. This can include text generation, summarization, classification, or other outputs depending on the model. Steps: Initialization. The tool initializes a connection to Google Vertex AI using the provided project ID and location. This establishes access to the model garden and the chosen pre-trained model. Model loading. The tool loads the specified model from the Vertex AI model garden. This involves retrieving the model's configuration and deployment details for execution. Input processing. The tool preprocesses the input data, if necessary, to ensure compatibility with the selected model's requirements. This might include formatting or tokenization. Model execution. The tool sends the processed input data to the loaded Vertex AI model. This initiates the model's prediction process, generating an output based on the model's trained capabilities. Output formatting. The tool formats the output from the Vertex AI model into a suitable representation for the Langchain chain. This might involve post-processing or conversion to a specific data structure. Metrics. Model performance evaluation. Metrics like accuracy, precision, recall, and F1 score are used to gauge the model's performance on the specific task. These metrics can vary depending on the chosen model and its intended purpose. Model latency. The time taken for the model to generate an output after receiving the input is a key metric for assessing model responsiveness. Resource consumption. The amount of computational resources CPU, memory required by the model during execution is considered for efficiency and cost optimization. Visualization plots. Model performance trends. Plots visualizing the evolution of model performance metrics over time, revealing potential improvements or degradation. Resource utilization charts. Plots showing the usage of computational resources CPU, memory over time, identifying any bottlenecks or areas for optimization. Model prediction distribution. Plots visualizing the distribution of model predictions for different input categories or scenarios, providing insights into model behavior. Fine-tune parameters. Temperature. This parameter controls the creativity and randomness of the model's output, with higher values indicating more creative and unpredictable results. Top. This parameter limits the probability distribution of the model's output, favoring more likely tokens, potentially leading to more coherent and focused responses. Max tokens. This parameter restricts the maximum number of tokens generated by the model, controlling the length of the output. Uncertainty methods. Confidence scores. The tool can leverage model-specific confidence scores to indicate the certainty of the model's predictions. Ensemble methods. Using multiple models or versions of the same model to generate predictions and aggregating them can provide a measure of prediction uncertainty. Challenges and fixes. Challenge 1. Accessing Vertex AI model garden. Sample use case. Attempting to utilize a pre-trained model without proper authentication or authorization to access the Google Cloud project containing the model. Fixes. Ensure that the correct project ID and location are provided. Configure proper authentication credentials for accessing Google Cloud services. Challenge 2. Model compatibility. Sample use case using a model that doesn't support the desired task or input format, leading to errors or unexpected outputs. Fixes. Carefully select the appropriate model based on its intended purpose and supported input formats. Pre-process inputs to meet the model's requirements. Challenge 3. Model latency. Sample use case experiencing high latency in model predictions due to factors like network connectivity or model complexity. Fixes. Optimize network connectivity for faster data transfer. Choose models with appropriate latency characteristics for the application. Explore options for model optimization or caching. Challenge 4. Resource consumption. Sample use case encountering high resource utilization, potentially leading to cost overruns or performance issues. Fixes. Select models with optimized resource consumption. Consider resource optimization techniques, such as model compression or using GPUs. Monitor resource usage and adjust model configuration or deployment settings as needed. Langchain Google Vertex Gemma messages to prompt. Description: this function converts a list of user messages to a prompt suitable for a language model. It takes a list of messages, each containing a user message and the model's response, and combines them into a single prompt. Inputs. Messages: a list of dictionaries, where each dictionary represents a message in the conversation. The dictionary should have two keys: user message and model response. The user message key contains the text of the user's message, and the model response key contains the text of the model's response. Outputs. Prompt: a string containing the final prompt that can be used to query the language model. Steps. The function iterates through the list of messages. For each message, it appends the user message and the model response to the prompt, separated by appropriate delimiters, e.g., user and model. The function adds a new line character after each message to separate the messages in the prompt. Metrics. None. Visualization plots. None. Fine-tune parameters. None. Uncertainty methods. None. Challenges and fixes. Challenge 1: the function may not be able to handle messages that contain special characters or formatting. Sample use case that resulted in challenge 1: a user message containing HTML tags. Fixes to challenge 1: escape special characters before adding them to the prompt. Challenge 2: the function may not be able to handle messages that are very long. Sample use case that resulted in challenge 2: a user message containing a long story. Fixes to challenge 2: truncate long messages before adding them to the prompt. Langchain Google Vertex LLMs. Description: explain in detail. The Langchain Google Vertex AI LLM is a powerful tool that integrates the functionality of Langchain with Google Vertex is pre-trained and custom large language models. It allows users to leverage the capabilities of Vertex models within their Langchain applications, enabling complex tasks like text summarization, question answering, and content generation. Inputs. Input 1: explain in detail text input: the text data that the LLM will process. This can include strings, lists of strings, or even files containing text. Input 2: explain in detail model specification: the user provides details about the specific Vertex AI model they wish to use, such as the model name, region, and version. Outputs. Output 1: explain in detail text output: the LLM's generated output based on the provided input and the selected Vertex AI model. This can include summaries, responses to questions, or even creative content. Output 2: explain in detail model metrics depending on the model used. The LLM can provide metrics like probability scores, confidence levels, or other relevant data related to the model's prediction. Steps. Step 1: explain in detail initialization: the Langchain Google Vertex AI LLM is initialized with the necessary credentials and information to access the Vertex AI service. Step 2: explain in detail model selection: the user selects the desired Vertex AI model from a list of available pre-trained models or a custom model they've previously trained. Step 3: explain in detail text input: the user provides the text data that the LLM will process. Step 4: explain in detail model prediction: the LLM sends the text input to the selected Vertex AI model for processing, and receives the output from the model. Step 5. Explain in detail output, handling the LLM formats and returns the model's output in a user-friendly way, potentially including additional information like metrics. Metrics. Metric 1. Explain in detail model accuracy, measures the model's performance on specific tasks, like text classification or question answering. Metric 2. Explain in detail latency, measures the time taken for the model to process the input and generate output. Metric 3. Explain in detail cost, tracks the computational resources consumed during model execution, potentially factoring in the Vertex AI service usage charges. Visualization plots. Visualization plot 1. Explain in detail performance plots, visualizations to understand how a model's accuracy, latency, and other metrics change over time or with different input parameters. Visualization plot 2. Explain in detail model confidence visualizations, showcasing the confidence level of the model's predictions for different inputs. Fine-tune parameters. Parameter 1. Explain in detail temperature, adjusts the randomness of the model's output, with higher values leading to more creative or diverse responses. Parameter 2. Explain in detail top K, limits the number of possible words considered by the model during generation, potentially influencing the output's coherence. Parameter 3. Explain in detail top, controls the probability distribution of the model's output, allowing for more focused or diverse outputs depending on the setting. Uncertainty methods. Uncertainty method 1. Explain in detail confidence scores. The LLM can provide confidence scores for its outputs, indicating the degree of certainty in its predictions. Uncertainty method 2. Explain in detail ensemble methods, using multiple Vertex AI models for prediction and combining their outputs can provide a measure of uncertainty by identifying discrepancies between the models. Challenges and fixes. Challenge 1. Explain in detail high latency. The model processing time might be slow, especially when dealing with large text inputs or complex tasks. Sample use case that resulted in challenge 1. A user attempting to summarize a lengthy research paper experienced significant delay in receiving the output. Fixes to challenge 1. Optimizing model choice, selecting a model specifically designed for fast processing or using a smaller model that is appropriate for the task. Input preprocessing, breaking down the input into smaller chunks or using techniques like summarization to reduce the input size. Vertex AI service optimization, adjusting the configuration of the Vertex AI service, potentially by scaling up the resources allocated to the model. Challenge 2. Explain in detail inconsistent output quality. The quality of the model's output might vary depending on the input and the model's specific training data. Sample use case that resulted in challenge 2. A user asked a question about a specific historical event, and the model provided an incorrect or irrelevant response. Fixes to challenge 2. Model fine-tuning, training the model on specific data relevant to the user's needs can improve performance for their domain of interest. Prompt engineering, crafting clear and specific prompts can help guide the model towards providing more accurate and relevant outputs. Evaluation and feedback, evaluating the model's performance on similar tasks and providing feedback can help identify areas for improvement and guide further model training. Challenge 3. Explain in detail cost considerations, using Vertex AI models can incur costs based on the model's usage and the resources consumed. Sample use case that resulted in challenge 3. A user ran a large-scale text generation task using a powerful Vertex AI model, resulting in a significant cost for the service. Fixes to challenge 3. Model selection, choosing a model that balances performance with cost effectiveness, potentially opting for a less computationally expensive model for specific tasks. Resource optimization: tuning the Vertex AI service configuration to utilize appropriate resources based on the task's demands. Minimizing unnecessary spending. Monitoring and budgeting: regularly monitoring the service usage and cost. Setting budgets and adjusting the approach if needed. Langchain Google Vertex Model Garden. Description: the Langchain Google Vertex AI Model Garden provides a comprehensive framework for building, deploying, and managing large language models (LLMs) on Google Cloud Platform (GCP. It leverages the power of Vertex AI, Google's managed machine learning service, to streamline the entire LLM lifecycle, from training and fine-tuning to deployment and monitoring. The Model Garden facilitates the use of various LLMs, including open-source models and custom models, enabling developers to seamlessly integrate these models into their applications. Inputs. Training data: the Model Garden requires a substantial amount of text data for training LLMs. The data should be relevant to the intended use case of the model and should be properly formatted and pre-processed to ensure optimal training. Model configuration: this input specifies the chosen LLM architecture, hyperparameters, and other configuration settings for the model training process. The configuration should be carefully tuned to achieve the desired performance and accuracy for the specific application. Evaluation metrics: the Model Garden requires defining evaluation metrics to assess the performance of the trained LLM. These metrics should be aligned with the target goals of the application, such as accuracy, coherence, or fluency. Outputs. Trained LLM: the Model Garden outputs a trained LLM that is ready to be deployed and used for inference. The trained model is stored in a Google Cloud Storage bucket for easy access and deployment. Model evaluation results: the Model Garden provides comprehensive evaluation results, including metrics and visualizations, to understand the performance of the trained LLM. This information helps in identifying areas for improvement and optimizing the model. Steps. Model selection: the first step involves choosing an appropriate LLM architecture based on the specific requirements of the application. The Model Garden provides access to a wide range of LLMs, including pre-trained models from Hugging Face, Google's own models, and custom models. Data preprocessing: the training data is preprocessed to ensure quality and consistency. This includes cleaning the data, removing irrelevant information, and preparing it for model training. Model training: the chosen LLM is trained using the preprocessed data on Vertex AI. The Model Garden provides various training options, including distributed training and hyperparameter tuning, to optimize the training process. Model evaluation: the trained LLM is evaluated using the defined metrics to assess its performance. The Model Garden provides various evaluation tools and visualization capabilities to analyze the results and identify areas for improvement. Model deployment: the trained LLM is deployed to Vertex AI for inference. The Model Garden facilitates seamless deployment and scaling of the model for real-time or batch predictions. Model monitoring: the deployed LLM is continuously monitored for performance and drift. The Model Garden provides tools for tracking metrics, detecting changes in performance, and retraining the model as needed to maintain optimal accuracy. Metrics. Accuracy: the accuracy of the LLM is measured using various metrics, such as perplexity, blue score, and rouge score, depending on the specific task. Coherence: the coherence of the LLM's output is evaluated by assessing the logical flow and consistency of the generated text. Fluency. The fluency of the generated text is measured by evaluating the grammatical correctness and readability of the output. Latency. The latency of the LLM is measured as the time taken to process a request and return a response. This metric is crucial for applications requiring real-time responses. Visualization plots. Confusion matrix. A confusion matrix visualizes the performance of the LLM by showing predicted and actual classes for different input examples. Attention heat maps. Attention heat maps visualize the attention mechanism used by the LLM, highlighting the parts of the input text that the model focuses on during inference. Loss curves. Loss curves plot the training loss over time, providing insights into the model's learning process and its convergence. Fine-tune parameters. Learning rate. The learning rate controls the step size during model optimization. A higher learning rate results in faster learning but can lead to instability, while a lower learning rate ensures stability but can lead to slower convergence. Batch size. The batch size specifies the number of training examples used in each update of a model's parameters. A larger batch size can lead to faster training but requires more memory, while a smaller batch size can be more memory efficient but slower to train. Number of epochs. The number of epochs specifies the number of times the model is trained on the entire dataset. More epochs can lead to better model performance but can also lead to overfitting. Uncertainty methods. Monte Carlo dropout. This method uses dropout during inference to estimate the uncertainty of a model's predictions. Bayesian neural networks. This method incorporates prior knowledge into the model parameters to estimate uncertainty. Challenges and fixes. Challenge 1. Limited data availability. Training a high-performing LLM requires a vast amount of high-quality training data. If the available data is limited, the model may not generalize well to unseen examples. Sample use case that resulted in Challenge 1. Training a chatbot for a niche industry with limited publicly available data. Fixes to Challenge 1. Use data augmentation techniques to increase the size of the training dataset. Leverage transfer learning to fine-tune a pre-trained LLM on the limited data. Or consider using a smaller LLM architecture that requires less data. Challenge 2. Overfitting. If the model is trained for too long or with a large learning rate, it may overfit the training data and fail to generalize well to new examples. Sample use case that resulted in Challenge 2. Training a language translation model that performs well on the training dataset but struggles with unseen languages. Fixes to Challenge 2. Use regularization techniques to prevent overfitting, such as dropout or weight decay. Monitor the model's performance on a validation set to detect overfitting early, and use early stopping to terminate the training process when performance on the validation set starts to decline. Challenge 3. Computational resources. Training and deploying LLMs can be computationally expensive, requiring significant resources in terms of memory, processing power, and storage. Sample use case that resulted in Challenge 3. Training a large language model for generating creative content, which requires significant computational resources. Fixes to Challenge 3. Utilize Google Cloud Platform's powerful infrastructure, such as TPUs or GPUs, to accelerate the training process. Consider using smaller LLM architectures that require fewer resources, or explore alternative training methods like federated learning to distribute the training workload across multiple devices. Challenge 4. Explainability. Understanding how an LLM makes decisions can be challenging due to its complex architecture and the vast amount of data it processes. Sample use case that resulted in Challenge 4. Debugging an LLM that generates biased or offensive Content, where it is crucial to understand the model's decision-making process to address the issue. Fixes to challenge 4. Use techniques such as attention visualization to understand which parts of the input text the model focuses on during inference. Analyze the model's gradients to identify sensitive features that may contribute to bias. And consider using more transparent model architectures that are easier to interpret. Challenge 5. Security. LLMs can be vulnerable to security attacks, such as adversarial attacks, where malicious actors try to manipulate the model's output. Sample use case that resulted in Challenge 5: deploying a chatbot for customer service, where a malicious actor could try to elicit sensitive information from the chatbot or manipulate its responses to mislead customers. Fixes to Challenge 5: implement robust input sanitization and validation measures to prevent malicious inputs from reaching the model. Regularly monitor the model for signs of adversarial attacks, and use techniques like adversarial training to make the model more resilient to attacks. Langchain Google Vertex Model Garden Chat Anthropic Vertex. Description: this model garden utilizes the Chat Anthropic Vertex model from Google Vertex AI to provide a powerful and efficient way to interact with large language models (LLMs). The model leverages the capabilities of Anthropic's Claude LLM, hosted on Google Cloud, for enhanced text generation, conversation, and other NLP tasks. Inputs: text. The input text to be processed by the model. This can be a question, a prompt, a piece of text for summarization, or any other text-based input. Parameters: optional parameters that control the model's behavior. These can include temperature, top, and other parameters that influence the model's output. Outputs: text. The output generated by the Chat Anthropic Vertex model based on the input text and parameters. This can be a response to a question, a generated text, a summary, or other forms of text output. Steps: initialize the Chat Anthropic Vertex model instance from the Google Vertex AI service. Send the input text and parameters to the model. Receive and process the generated output from the model. Metrics: accuracy. Evaluate the model's accuracy in performing tasks like question answering, summarization, and text generation. Coherence: measure the coherence and fluency of the generated text. Relevance: assess the relevance of the model's output to the input prompt or question. Visualization plots. Confusion matrix: if applicable, visualize the model's accuracy in classifying different categories or labels. Attention maps: if applicable, visualize the attention weights of the model to understand how it focuses on specific parts of the input text during processing. Fine-tune parameters. Learning rate: the rate at which the model's parameters are adjusted during training. Batch size: the number of examples processed at each step during training. Number of epochs: the number of times the training dataset is iterated through during training. Uncertainty methods. Confidence scores: the model can provide confidence scores for its predictions, indicating the level of certainty in its output. Ensemble methods: combining multiple models to reduce uncertainty and improve predictions. Challenges and fixes. Challenge 1: limited context window: the model may have difficulty handling long input texts, exceeding its context window size. Sample use case that resulted in Challenge 1: attempting to summarize a lengthy document that exceeds the context window limit. Fixes to Challenge 1: break down the input text into smaller chunks or use a model with a larger context window. Challenge 2: bias in training data: the model may exhibit biases present in the training data, leading to unfair or discriminatory outputs. Sample use case that resulted in challenge 2 generating biased text or making discriminatory predictions due to biases present in the training data. Fixes to challenge 2 use diverse and representative training data. Implement bias mitigation techniques. And monitor for bias during model development and deployment. Langchain Google Vertex Model Garden Vertex AI Model Garden. Description: the Vertex AI Model Garden component of Langchain enables seamless interaction with Google. Vertex is powerful model capabilities within the context of Langchain chains. It essentially acts as a bridge between Langchain and Vertex AI, allowing you to leverage pre-trained or custom models from Vertex AI within your Langchain workflows. This opens up a vast range of possibilities, including integrating advanced language models, image analysis tools, and more, directly into your Langchain applications. Inputs. Input 1: the input to the Vertex AI model. This can be text, images, or other data depending on the specific model being used. Input 2: optional, depending on the specific Vertex AI model. There may be additional inputs such as parameters or configurations that can be provided. Outputs. Output 1: the primary output from the Vertex AI model. This could be text, predictions, classifications, or other data relevant to the model's function. Output 2: optional, depending on the specific Vertex AI model. There might be additional outputs such as confidence scores, probabilities, or other information related to the model's predictions. Steps. Step 1: the Langchain chain receives the input data. Step 2: the Vertex AI Model Garden component prepares the input data according to the requirements of the chosen Vertex AI model. Step 3: the component calls the Vertex AI model, sending the prepared input data. Step 4: the component receives the output from the Vertex AI model and processes it into a format suitable for use by the Langchain chain. Step 5: the Langchain chain receives the processed output from the Vertex AI Model Garden component and uses it for further processing or as a final result. Metrics. Metric 1: model performance metrics, e.g., accuracy, precision, recall, F1 score are retrieved from Vertex AI and reported for evaluation. Metric 2: inference time is tracked to assess the efficiency of model execution within a Langchain workflow. Visualization plots. Visualization plot 1: model performance plots, e.g., ROC curve. Precision recall curve can be generated based on the metrics retrieved from Vertex AI. Visualization plot 2: inference time visualizations can help identify performance bottlenecks and optimize model usage within Langchain. Fine-tune parameters. Parameter 1: model name. This parameter defines the specific Vertex AI model to be used in a Langchain chain. It can refer to a pre-trained model from Vertex's Model Garden or a custom model deployed on Vertex AI. Parameter 2: version. Optionally, you can specify the version of the Vertex AI model to be used. This ensures that the chain consistently utilizes the desired version of the model. Uncertainty methods. Uncertainty method 1: confidence scores provided by the Vertex AI model can be used to quantify a model's uncertainty in its predictions. Uncertainty method 2: Bayesian methods or other approaches may be implemented to estimate model uncertainty for more complex scenarios. Challenges and fixes. Challenge 1: input data format incompatibility. The input format required by the Vertex AI model may not match the format produced by the preceding components in the Langchain chain. Sample use case that resulted in challenge 1: a Langchain chain might produce text output, but the Vertex AI model expects image data as input. Fixes to challenge 1. Pre-process the data using Langchain components to convert it to the appropriate format before sending it to the Vertex AI model garden. Challenge 2. Output interpretation. The output from the Vertex AI model might need further processing or interpretation to be meaningful in the context of the Langchain chain. Sample use case that resulted in challenge 2. The Vertex AI model returns a probability distribution, but the Langchain chain requires a specific class label as output. Fixes to challenge 2. Incorporate logic within the Langchain chain to process the output and extract the desired information from the Vertex AI model's results. Langchain Google Vertex Vector Stores. Description: the Langchain Google Vertex AI Vector Store allows you to store and retrieve embeddings within Google Cloud's Vertex AI platform. This is a powerful combination, enabling you to leverage the robust features of Vertex AI, such as scalability, security, and managed infrastructure, for your embedding-based applications. Inputs. Embedding model. This input is a pre-trained embedding model that maps text into numerical vectors. The model can be chosen from Google's selection of Vertex AI pre-trained models or a custom model. You have uploaded data, the text data you want to embed and store in the vector store. This can be a list of strings, a text file, or any other data format that can be processed by the chosen embedding model. Vertex AI endpoint. A Vertex AI endpoint where the embedding model is deployed. This provides the necessary infrastructure to process the input data and generate embeddings. Outputs. Vector store. A Vertex AI vector store containing the embedded data. This vector store acts as a searchable index, allowing efficient retrieval of similar documents based on the cosine similarity between their embeddings. Steps. Create an embedding model on Vertex AI. Select or upload a pre-trained embedding model from a Vertex AI model garden or create your own custom model. Deploy this model to a Vertex AI endpoint. Create a vector store on Vertex AI. Specify the Vertex AI endpoint where your embedding model is deployed, along with the data you want to embed. Langchain will automatically handle the interaction with Vertex AI to create the vector store. Index your data. The chosen embedding model will be used to generate embeddings for each input. Document. These embeddings are stored in the vector store. Search the vector store for a given query. Langchain will first use the embedding model to generate an embedding for the query. It then uses cosine similarity to find the closest embeddings within the vector store, returning the corresponding documents. Metrics. Cosine similarity measures the similarity between the query embedding and the embeddings of documents in the vector store. Higher cosine similarity indicates a stronger match. Retrieval accuracy evaluates the effectiveness of the vector store in retrieving relevant documents for a given query. Visualization plots. Retrieval distribution. This plot visualizes the distribution of cosine similarity scores between the query embedding and the embeddings of retrieved documents. Embedding space visualization. If the embedding dimensionality is low enough, a visualization of the embeddings can be created to show the relative positions of different documents in the embedding space. Fine-tune parameters. Embedding model. Different embedding models may be more suitable for specific tasks or datasets. Dimensionality reduction techniques like PCA or T-SNE can be used to reduce the dimensionality of the embeddings for faster retrieval or visualization. Distance metric. Explore different distance metrics beyond cosine similarity, such as Euclidean distance or Manhattan distance. Uncertainty methods. Confidence scores. The model can provide confidence scores for retrieved documents. indicating the likelihood of their relevance. Ensemble methods using multiple embedding models or different distance metrics can create an ensemble model, reducing uncertainty by combining predictions. Challenges and fixes. Challenge 1: high latency during retrieval. The latency of retrieving embeddings from Vertex AI can be high due to network traffic or resource limitations. Sample use case that resulted in Challenge 1: a user submitted a query to a large dataset stored in a Vertex AI vector store, resulting in a noticeable delay before receiving results. Fixes to Challenge 1: optimize the embedding model. Choose a more efficient embedding model or reduce the dimensionality of the embeddings to decrease the computational overhead. Increase Vertex AI resources. Allocate more resources to the Vertex AI endpoint where the embedding model is deployed, potentially using a more powerful machine type or scaling up the number of instances. Use a caching mechanism. Implement a caching layer to store recently retrieved embeddings, reducing the number of calls to Vertex AI. Challenge 2: difficulty in managing multiple vector stores. Tracking and managing multiple vector stores across different Vertex AI projects can be cumbersome. Sample use case that resulted in Challenge 2: an organization used multiple vector stores for different datasets, but struggled to maintain consistency and track their performance across projects. Fixes to Challenge 2: use a central repository. Utilize a centralized repository, such as a database or configuration management system, to manage the metadata and locations of different vector stores. Implement version control. Use version control to track changes to the vector stores and ensure consistency between deployments. Create a monitoring dashboard. Develop a monitoring dashboard to track the performance and health of all vector stores within the organization. Langchain Google Vertex Vector Stores. Document storage. Data store. Document storage description: the data store document storage class from Langchain is a document storage implementation specifically designed for storing and retrieving documents within a Google Vertex AI data store. It leverages the power of Vertex's scalable and reliable data storage capabilities to manage your documents. Inputs. Project: the Google Cloud Project ID where your Vertex AI data store resides. Location: the Google Cloud region where your Vertex AI data store is located. Datastoid: the unique identifier of the Vertex AI data store you want to use for document storage. Entity type: the type of entity document you'll be storing in the data store. It acts as a category or label for your documents. Embedding function: a function that takes a document's content and returns a vector representation. This is essential for indexing and searching your documents based on their content similarity. Outputs: a data store document storage object that provides methods for storing, retrieving, and deleting documents within your specified Vertex AI data store. Steps: initialization: the data store document storage is initialized with the provided project. Location: data store ID, entity type, and embedding function. Document storage: when you use the add method, it takes a document as input, generates its embedding using the provided embedding function, and stores the document and its embedding into the data store. Document retrieval: the search method allows you to retrieve documents from the data store based on similarity to a query vector. It uses the embedding function to generate a vector representation of your query and then searches the data store for documents with similar embeddings. Document deletion: the delete method enables you to remove documents from the data store based on their unique identifier. Metrics: storage capacity: the total amount of data documents stored in your Vertex AI data store. This metric provides insights into how much storage space your documents consume. Query latency, the average time it takes to retrieve documents based on similarity searches. This metric reflects the efficiency and speed of your document retrieval process. Visualization plots. Document distribution, a visualization of the distribution of documents within your data store based on their content similarity. This plot can reveal patterns and clusters in your document collection. Fine-tune parameters. Embeddings model, you can experiment with different embedding models, e.g. sentence transformers. OpenAI's text embedding ADA002 to optimize the quality of your document similarity calculations. Search algorithm. Vertex AI data store provides different search algorithms, e.g. Euclidean distance, cosine similarity that can be fine-tuned for specific search scenarios. Indexing options, you can adjust indexing settings in Vertex AI data store to balance retrieval speed and storage efficiency. Uncertainty methods. Confidence scores. Some embedding models provide confidence scores for each generated vector. You can leverage these scores to assess the reliability of similarity results. Query expansion. Experimenting with different query expansions, e.g. adding related keywords, can help improve the accuracy and comprehensiveness of document retrieval. Challenges and fixes. Challenge 1. Inefficient embedding generation. If the chosen embedding model is computationally expensive or slow, it can impact the performance of document storage and retrieval. Sample use case. A large collection of documents is being processed, and the embedding function takes a long time to generate vectors for each document. Fixes. Consider using more efficient embedding models or optimizing the embedding generation process, e.g. parallel processing, caching. Challenge 2. High search latency. If the data store is not properly indexed or optimized for search, retrieval operations can become slow. Sample use case. A user performs a similarity search, but the results take an unacceptable amount of time to return. Fixes. Fine-tune indexing parameters within Vertex AI data store. Optimize the search algorithm, or consider using a specialized search engine if performance is critical. Challenge 3. Document storage limits. Vertex AI data store has limits on the size and number of documents that can be stored. Sample use case. An application attempts to store a massive document collection, exceeding the storage limits of the data store. Fixes. Consider using multiple data stores or implementing a document chunking strategy to break large documents into smaller units. Langchain Google Vertex vector stores document storage. Description. The document storage class from the Langchain Google Vertex library provides a method to store and retrieve documents within Google Vertex AI. It acts as a bridge between Langchain's document processing capabilities and the powerful data management features of Vertex AI. Inputs. Document. This input is a list of documents, each represented as a dictionary with the following structure. Page content. The actual text content of the document. Metadata. A dictionary containing additional metadata about the document, such as its source, author, or creation date. Endpoint name. The name of the Google Vertex AI endpoint where the vector store is deployed. This endpoint serves as the access point for storing and retrieving documents. Outputs. Document storage. The document storage object is instantiated with the provided inputs and is ready to store and retrieve documents within Vertex AI. Steps. Instantiate the document storage object with the provided endpoint name. The object uses the Vertex AI API to interact with the specified endpoint. It takes the input documents and converts them into a format suitable for storage within Vertex AI. The document storage object then stores the documents within the Vertex AI endpoint, ensuring their accessibility for later retrieval. Metrics: storage efficiency, the effectiveness of compressing and storing documents within Vertex AI. Minimizing storage space utilization. Retrieval latency, the time taken to retrieve documents from Vertex AI. Considering factors like data volume and endpoint performance. Endpoint availability, the reliability of the Vertex AI endpoint for storing and retrieving documents, measured by uptime and potential outages. Visualization plots. Document distribution, a visualization that shows the distribution of documents based on their content or metadata. Retrieval latency, a plot that represents the latency experienced during document retrieval over time, highlighting potential performance issues. Endpoint utilization, a visualization that tracks the usage of the Vertex AI endpoint, indicating how actively it is being accessed. Fine-tune parameters. Indexing strategy, the method used to index the documents within Vertex AI, influencing retrieval accuracy and efficiency. Metadata fields, the specific metadata fields that should be stored along with each document, allowing for more targeted retrieval. Data partitioning, the way the documents are divided and stored within the Vertex AI endpoint, impacting retrieval performance and scalability. Uncertainty methods. Retrieval confidence, the ability to assess the confidence level in the retrieved documents based on their relevance and similarity to the search query. Data completeness, a mechanism to measure the extent to which the available documents cover a desired information space, potentially indicating gaps or missing information. Challenges and fixes. Challenge 1: managing large document volumes. Storing and retrieving large volumes of documents can lead to performance issues and increased latency. Sample use case: a knowledge base with millions of documents, requiring efficient storage and retrieval. Fixes: use data partitioning strategies to divide documents across multiple storage units, improving parallel access. Optimize the indexing strategy to prioritize efficient retrieval based on content and metadata. Challenge 2: ensuring data security. Protecting sensitive document content within Vertex AI is crucial to prevent unauthorized access or data breaches. Sample use case: storing confidential customer records or proprietary research data. Fixes: leverage Vertex's built-in security features, such as access control lists and encryption at rest. Implement robust authentication and authorization mechanisms to restrict access to authorized users. Challenge 3: integrating with other tools. Seamlessly integrating the document storage object with other Langchain components is essential for building end-to-end document processing pipelines. Sample use case: combining document retrieval with language models for question answering or summarization. Fixes: ensure compatibility between the document storage object and other Langchain components. Minimizing code modifications. Utilize Langchain's built-in integration features to connect different modules efficiently. Langchain Google Vertex Vector Stores Document Storage (GCS) Document Storage. Description: GCS Document Storage is a Langchain document storage class that allows you to store and retrieve documents from Google Cloud Storage (GCS). It is designed to work with the Vertex AI Vector Store, which allows you to perform similarity search on your stored documents. Inputs: GCS bucket. Name the name of the GCS bucket where you want to store your documents. GCS path. The path within the GCS bucket where you want to store your documents. Document loader. A Langchain document loader that can be used to load the documents from your data source, e.g., a CSV file. A directory of text files. etc. Outputs. Stored documents. The documents that have been stored in the GCS bucket. Document IDs. The unique identifiers that are assigned to each document. Steps. Create a GCS document storage object. Initialize the object with the required input parameters. Bucket name. GCS path. Document loader. Load documents. Use the document loader to load the documents from your data source. Store documents in GCS. Store each document in the GCS bucket at the specified path. Generate document IDs. Assign unique identifiers to each document and store them along with the document content in GCS. Metrics. Storage efficiency. The amount of storage space used to store the documents in GCS. Retrieval speed. The time it takes to retrieve a specific document from GCS. Visualization plots. Storage usage. A chart showing the amount of storage space used by the GCS bucket over time. Document retrieval time. A chart showing the time it takes to retrieve documents from GCS for different document sizes. Fine-tune parameters. Non-GCS document storage does not have any fine-tune parameters. Uncertainty methods. Non-GCS document storage does not have any uncertainty methods. Challenges and fixes. Challenge 1. Accessing GCS bucket with insufficient permissions. Sample use case that resulted in challenge 1. Attempting to store documents in a GCS bucket without the necessary access permissions. Fixes to challenge 1. Ensure that the service account used by the Langchain application has the required permissions to access the GCS bucket, e.g. read-write permissions. Challenge 2. GCS bucket is in a different region than the Vertex AI vector store. Sample use case that resulted in challenge 2. Storing documents in a GCS bucket in a different region than the Vertex AI vector store, resulting in slow retrieval times due to increased network latency. Fixes to challenge 2. Store the documents in a GCS bucket that is in the same region as the Vertex AI vector store. Challenge 3. Slow document retrieval time due to large file sizes. Sample use case that resulted in challenge 3. Attempting to retrieve large documents from GCS, resulting in long retrieval times. Fixes to challenge 3. Optimize the document loading process by using a faster document loader, or by splitting large documents into smaller chunks. Langchain Google Vertex vector stores. Vector stores. Vector search. Vector store. Description. The vector search vector store class is a vector store implementation for Langchain that leverages Google Vertex's vector search service. This service allows you to perform similarity searches on large datasets of vectors, which is crucial for various tasks like semantic search, recommendation systems, and more. Inputs. Embedding function. A function that converts text into a numerical vector representation. Langchain provides various embedding functions, or you can define your own. Google Vertex AI endpoint. The endpoint of your deployed Vertex AI vector search model, which is responsible for handling vector operations and similarity searches. Outputs. Vector data. This represents the embeddings of your data stored in the vector search vector store. Similarity search results when you perform a similarity search using the similarity search method. The output will be a list of the most similar items vectors from your stored data based on the query vector. Steps. Initialization. Create an instance of the vector search vector store class. You'll need to provide the embedding function, Vertex AI endpoint, and other optional parameters like the project and location. Add data. Call the add method to add new data to the vector store. This involves converting your data to vectors using the embedding function and sending them to Vertex AI for storage. Similarity search. Use the similarity search method to find the most similar items to your query. This involves converting the query text to a vector, sending it to Vertex AI, and retrieving the top k similar vectors from your stored data. Metrics. Search time. The time taken to complete a similarity search, which is highly influenced by the size of your dataset and the efficiency of the Vertex AI vector. Search service. Accuracy. This refers to the quality of the search results, measured by how relevant the retrieved items are to the query. Visualization plots. Scatter plot. Visualize your vector data in a low-dimensional space 2D or 3D, showing the relationships between different points vectors. Similarity heat map. Create a heat map showing the similarity scores between your query vector and all the other stored vectors. This can help you understand the distribution of similarity scores. Fine-tune parameters. Similarity metric. Choose a similarity metric, like cosine similarity or Euclidean distance, based on your data and the type of search you want to perform. Indexing strategy. Select an indexing strategy for Vertex AI that suits your specific data, characteristics and search requirements. Query expansion. Explore techniques like keyword expansion or semantic query expansion to improve the quality of your search results. Uncertainty methods. Confidence scores. Vertex AI might provide confidence scores along with search results, indicating the level of certainty for each returned item. Alternative results. Consider retrieving and displaying alternative search results to provide a broader range of possibilities for users. Challenges and fixes. Challenge 1. Long search times for large datasets. Sample use case that resulted in challenge 1 when dealing with millions or billions of data points. The search process can take a significant amount of time. Fixes to challenge 1. Optimize the Vertex AI vector search model by tuning indexing parameters and choosing appropriate data partitioning strategies. Explore using techniques like approximate nearest neighbor search and for faster search. Trading some accuracy for speed. Challenge 2. Handling dynamic updates. Sample use case that resulted in challenge 2. If your data is constantly changing, efficiently updating the vector store and the Vertex AI model can be challenging. Fixes to challenge 2. Explore techniques like incremental indexing, where only changes to the data are added to the vector store. Use Vertex AI model update features to efficiently retrain or update the model when necessary. Langchain. Google Vertex vector stores. Vector stores. Vector search. Vector store. Data store. Description. The vector search vector store data store class in Langchain is a specialized vector store designed for efficient similarity search using Google Vertex AI. It leverages the power of Vertex AI's vector search capabilities to retrieve relevant documents based on their embeddings. Inputs. Embeddings. A list of embeddings representing the data you want to store in the vector store. Each embedding is typically a numerical representation of a text document, image, or other data. Metadata. A dictionary containing metadata associated with each embedding. This metadata provides additional context and information about the data. Vertex AI endpoint. The Vertex AI endpoint where the vector search index is deployed. Outputs. Similarity search. The similarity search method returns a list of documents ranked by their similarity to a given query embedding. This enables efficient retrieval of relevant information based on semantic similarity. Steps. Embedding generation. The input data is first transformed into numerical embeddings using a suitable embedding model. Vertex AI index creation. The embeddings and metadata are used to create a vector search index on the Vertex AI platform. This index is optimized for efficient similarity search. Query processing. When a query is submitted, It is first embedded using the same embedding model. Similarity search. The query embedding is then used to perform similarity search against the Vertex AI index, returning the most relevant documents. Metrics. Recall the percentage of relevant documents that are retrieved by the similarity search. Precision. The percentage of retrieved documents that are relevant. Mean average precision map. A comprehensive measure that combines precision and recall at various recall levels. Visualization plots. Recall precision curve. A plot that shows the trade-off between precision and recall at different retrieval thresholds. Retrieval accuracy vs. query complexity. A plot that examines how the accuracy of the retrieval varies with the complexity of the query. Fine-tune parameters. Index parameters. The parameters used to configure the Vertex AI index, such as the embedding dimension, the number of shards, and the similarity metric. Query parameters. Parameters that control the search process, such as the number of results to retrieve, the similarity threshold, and the scoring function. Uncertainty methods. Confidence scores. The vector store can optionally provide confidence scores for each retrieved document, indicating the level of certainty about its relevance. Ensemble methods. Combining predictions from multiple models or indices can help reduce uncertainty and improve robustness. Challenges and fixes. Challenge 1. Cold start problem. When a new vector store is created, it initially has a limited number of data points, leading to lower retrieval accuracy. Sample use case that resulted in challenge 1. Trying to search a newly created vector store for a specific topic with limited data. Fixes to challenge 1. Gradually add more data to the vector store to improve its accuracy over time. Use a pre-trained embedding model that has been trained on a large dataset. Challenge 2. Data drift. The relevance of documents can change over time as the underlying data evolves. This can lead to inaccurate search results. Sample use case that resulted in challenge 2. A vector store used for product recommendations may become outdated as new products are launched and customer preferences change. Fixes to challenge 2. Regularly update the vector store with new data to account for data drift. Implement a mechanism to monitor the performance of the vector store and retrain the model if needed. Challenge 3. Scalability. Handling large datasets and complex queries can pose scalability challenges for vector search. Sample use case that resulted in challenge 3. A vector store used for search in a large e-commerce website with millions of products may struggle to provide fast and accurate results. Fixes to challenge 3. Utilize the distributed search capabilities of Vertex AI to handle large datasets. Optimize the index parameters and query parameters to improve performance. Langchain Google Vertex Vision Models. Description. Explain in detail. This module leverages Google Vertex's powerful vision models to perform various image-based tasks using Langchain. It allows you to harness the capabilities of pre-trained models for image classification, object detection, and more, seamlessly integrating them into your Langchain workflows. Inputs. Input 1. Explain in detail image data. The module takes an image as input, either as a file path, a URL, or a binary stream. Input 2. Explain in detail model parameters depending on the chosen vision model. You can specify various parameters such as model type, prediction threshold, and more. Outputs. Output 1. Explain in detail predictions. The module returns predictions based on the specified task, such as class labels with confidence scores for image classification or bounding boxes with labels for object detection. Output 2. Explain in detail metadata. The module might provide additional information about the Predictions, such as model version, prediction time, or other relevant details. Steps. Step 1. Explain in detail image preprocessing. The input image is preprocessed, including resizing, normalization, and converting to the expected format required by the vision model. Step 2. Explain in detail model prediction. The preprocessed image is fed into the chosen Vertex AI vision model, which generates predictions based on its training data. Metrics. Metric 1. Explain in detail accuracy. This metric measures how accurately the model classifies or detects objects in the image, typically calculated as the percentage of correct predictions. Metric 2. Explain in detail precision and recall. These metrics are relevant for object detection, evaluating the model's ability to correctly identify objects and avoid false positives negatives. Visualization plots. Visualization plot 1. Explain in detail image with bounding boxes for object detection tasks. The module can visualize the detected objects by drawing bounding boxes around them on the original image. Visualization plot 2. Explain in detail confusion matrix. This plot visually represents the model's performance by showing the distribution of true and false positive negative predictions. Fine-tune parameters. Parameter 1. Explain in detail model type. You can choose from a variety of pre-trained vision models offered by Vertex AI, each specialized for different tasks. Parameter 2. Explain in detail prediction threshold. This parameter allows you to adjust the confidence level required for a prediction to be considered valid, influencing the trade-off between precision and recall. Uncertainty methods. Uncertainty method 1. Explain in detail Monte Carlo dropout. This technique provides an estimate of model uncertainty by performing multiple forward passes with different random dropout patterns. Uncertainty method 2. Explain in detail ensemble methods by combining multiple models trained on different subsets of data. Ensemble methods can provide more robust predictions and assess uncertainty. Challenges and fixes. Challenge 1. Explain in detail image resolution mismatch. If the input image resolution differs significantly from the model's training data, it can lead to inaccurate predictions. Sample use case that resulted in challenge 1. Using a high-resolution image with a model trained on low-resolution images. Fixes to challenge 1. Resize the image to match the model's expected input resolution. Challenge 2. Explain in detail insufficient training data. If the model has not been trained on a sufficiently diverse set of images, it may struggle to generalize to new, unseen images. Sample use case that resulted in challenge 2. Using a model trained on a limited dataset of indoor scenes to predict objects in outdoor scenes. Fixes to challenge 2. Fine-tune the model on a larger dataset that includes a wider range of images representative of the target domain. Langchain Google Vertex Vision Models Vertex Image Captioning. Description. This Langchain integration leverages Google Vertex's image captioning API to generate textual descriptions for input images. Inputs. Image. A single image or a batch of images in a supported format, e.g. JPEG, PNG. Outputs. Caption. The generated textual description for the input image. Steps. Image preprocessing. The input image is preprocessed by Vertex AI to prepare it for the image captioning model. Model inference. The preprocessed image is passed to the Vertex AI image captioning model, which generates a textual caption. Metrics. Blue score measures the quality of the generated caption by comparing it to human-written reference captions. CIDR score evaluates the caption's coherence and fluency. Meteor score assesses the accuracy and relevance of the generated caption. Visualization plots. Image and caption visualization. The input image and generated caption are displayed together to provide a visual understanding of the model's output. Fine-tune parameters. Model selection. Choose a pre-trained image captioning model from Vertex AI. Uncertainty methods. Confidence score. The model provides a confidence score for the generated caption, indicating its level of certainty. Challenges and fixes. Challenge 1. Image quality. Low resolution or blurry images can affect the quality of the generated caption. Sample use case that resulted in challenge 1. A blurry photograph of a sunset resulted in a generic caption like a picture of a sunset. Fixes to challenge 1. Use high-quality images for input. If the image quality is poor, consider pre-processing steps like image sharpening or denoising. Challenge 2. Domain specificity. The model may struggle to generate accurate captions for images with specialized content. Sample use case that resulted in challenge 2. A medical image of a brain scan resulted in a caption like a picture of a brain. Fixes to challenge 2. Fine-tune the model on a data set of images from the specific domain. Use prompt engineering to provide context and keywords related to the domain. Challenge 3. Object recognition. The model may fail to accurately identify certain objects in the image, resulting in inaccurate captions. Sample use case that resulted in challenge 3. An image of a dog playing fetch with a stick was captioned as a picture of a dog playing with a stick. The model incorrectly identified the stick as a stick instead of a toy. Fixes to challenge 3. Pre-process the image to enhance object detection, potentially by using a separate object detection model. Ensure the dataset used for model training includes diverse examples of the relevant objects. Langchain Google Vertex Vision Models Vertex Image Editor Chat. Description: the Vertex AI Image Editor Chat model is a large language model that can be used to edit images in a conversational manner. Users can provide natural language prompts, such as "make the sky bluer," and the model will understand and apply the requested changes to the image. It leverages Google's advanced image editing capabilities and AI technology to provide a user-friendly and intuitive experience for image manipulation. Inputs: image: a digital image in a supported format, e.g., JPG, PNG. Prompt: a natural language text description of the desired image editing changes. Outputs: edited image: the modified image reflecting the requested changes. Steps: image encoding: the input image is encoded into a suitable representation that the model can process. Prompt understanding: the model analyzes the text prompt to identify the desired editing actions, such as color adjustments, object removal, or style transformations. Image editing: the model applies the appropriate image editing operations based on the prompt. Understanding: using its knowledge of image manipulation techniques. Output generation: the model generates the final edited image incorporating the applied changes. Metrics: image quality: evaluating the perceptual quality of the edited image, considering aspects like sharpness, color fidelity, and artifact reduction. Prompt understanding: accuracy: measuring how well the model interprets and correctly executes the user's editing intentions. Editing consistency: assessing the consistency of the applied editing changes across different image regions or elements. Visualization plots: edited image comparison: visualizing the original image side by side with the edited image to highlight the applied changes. Editing progress: showing intermediate stages of the editing process to illustrate the model's execution steps. Fine-tune parameters: prompt embedding weights: adjusting the weights of the prompt embedding layer to improve the model's ability to understand and process user prompts. Editing operation weights, fine-tuning the weights of different editing operations, e.g. color correction, object removal to optimize their performance. Uncertainty methods, confidence score, assigning a confidence score to the model's predictions, reflecting the uncertainty in its understanding of the prompt or the quality of the edited image. Region-wise uncertainty, providing uncertainty estimates for different image regions, indicating areas where the model might have difficulty applying edits accurately. Challenges and fixes. Challenge 1: ambiguous or complex prompts. Some prompts might be ambiguous or require a deeper understanding of the user's intent, leading to unexpected or incorrect edits. Sample use case that resulted in challenge 1: a prompt like "make the picture more vibrant" could be interpreted in multiple ways, depending on the context of the image. Fixes to challenge 1: incorporating context-aware mechanisms, using examples to clarify the user's intent, or providing options for the user to further specify the desired changes. Challenge 2: image artifacts or inconsistencies, applying edits to images with existing artifacts or inconsistencies might result in undesirable results or introduce new artifacts. Sample use case that resulted in challenge 2: editing an image with blurry regions could lead to the model amplifying the blur or introducing new artifacts in the edited regions. Fixes to challenge 2: employing advanced image denoising techniques or incorporating image quality assessment metrics into the model's decision-making process to minimize the introduction of artifacts. Challenge 3: limited editing capabilities. The model might not support all types of editing operations, such as complex object manipulation or advanced style transfer. Sample use case that resulted in challenge 3: attempting to seamlessly replace an object in an image with a new object might exceed the model's current capabilities. Fixes to challenge 3: expanding the model's editing capabilities by incorporating new techniques or training on a wider range of editing tasks. Challenge 4: maintaining image integrity. Editing images could lead to unintended consequences, such as distorting or altering the original image content in an undesirable way. Sample use case that resulted in challenge 4: attempting to remove an object from an image could result in unwanted distortions or the loss of important image details. Fixes to challenge 4: implementing robust image integrity checks, using techniques to preserve important features during editing, or providing options for enderado actions to allow users to revert changes. Langchain Google Vertex Vision Models Vertex Image Generator Chat. Description: this tool uses Google Vertex's image generation models to generate images based on text prompts. It uses the Vertex AI Chat API, which allows for more natural, conversational interactions with the model. Inputs: prompt: a textual description of the image to be generated. Outputs: image: a generated image based on the provided prompt. Steps: the provided prompt is sent to the Vertex AI Chat API. The API interprets the prompt and uses its underlying image generation model to generate an image. The generated image is returned to the user. Metrics: image quality assessed based on factors such as clarity, detail, and adherence to the prompt. Image diversity: how well the model can generate different images for similar prompts. Model performance measured based on generation time and resource utilization. Visualization plots: image comparison, visualizing side by side the generated image and the original prompt for a qualitative assessment. Prompt distribution, analyzing the types of prompts used to understand the model's strengths and weaknesses. Fine-tune parameters. Temperature controls the creativity of the generated image, with higher values producing more diverse and unexpected results. Top K determines the number of possible outputs considered by the model, influencing the diversity and quality of the generated images. Uncertainty methods. Confidence score. The model can provide a score indicating its confidence in the generated image, helping users assess its reliability. Multiple generations. Generating multiple images for the same prompt can highlight the model's uncertainty and diversity in its output. Challenges and fixes. Challenge 1. Difficulty in generating high-quality images that accurately reflect complex or abstract prompts. Sample use case. Generating an image of a philosophical concept or a dreamlike scene. Fixes. Providing more detailed and specific prompts. Utilizing different generation parameters, such as temperature and top. Employing techniques like image in painting to refine and improve the generated image. Challenge 2. Generating images with unintended biases or stereotypes. Sample use case. Prompting for an image of a doctor and receiving an image of a male doctor. Fixes. Training the model on a diverse dataset that includes images representing various genders, ethnicities, and backgrounds. Using prompt engineering techniques to mitigate bias, such as using neutral or inclusive language. Employing techniques like adversarial training to identify and correct biases in the generated images. Langchain Google Vertex Vision Models Vertex AI Visual Q&A Chat. Description: This Langchain agent combines the capabilities of Google Vertex AI's vision models in a conversational chat interface to enable users to ask natural language questions about images and receive comprehensive answers. It leverages the power of Vertex AI's image understanding models to extract information from images, and then uses a conversational chatbot to translate the extracted information into human understandable responses. Inputs: image and image file or URL that the agent will analyze. Question: a natural language question about the content of the image. Outputs: answer: a human readable text response answering the user's question based on the image analysis. Steps: image preprocessing: the provided image is preprocessed for optimal processing by the Vertex AI vision model. This may involve resizing, converting to grayscale, or other transformations. Image understanding: the preprocessed image is fed into a Vertex AI vision model, such as a pre-trained object detection or image classification model. The model analyzes the image and extracts relevant information, such as object labels, bounding boxes, or image-level classifications. Question: understanding: the user's natural language question is processed using a language model to extract the key concepts and entities relevant to the image content. Answer generation: the extracted information from the image and the question understanding process are combined to generate a comprehensive answer to the user's question. The agent may use knowledge bases, external APIs, or its own internal knowledge to provide a more informative answer. Metrics: accuracy: the agent's ability to provide correct and accurate answers based on the image content. This can be measured by comparing the generated answers with a ground truth set of answers. Coherence: the clarity and logical flow of the generated answers, ensuring they are understandable and easy to follow. Relevance: the ability of the agent to focus on the relevant aspects of the image in question, avoiding irrelevant information in its response. Visualization plots: image with highlighted objects: the agent can visualize the identified objects in the image by drawing bounding boxes around them with corresponding labels. Confidence scores: visualize the confidence scores associated with each object detection or classification prediction. Attention maps highlight the regions of the image that the model focused on while generating pay. Answer. This can provide insights into how the model arrived at its conclusion. Fine-tune parameters. Vertex AI model selection. The user can fine-tune the agent by selecting the most appropriate Vertex AI vision model for their specific image analysis needs. Chatbot personality. The user can adjust the chatbot's persona and conversational style to match their desired user experience. Uncertainty methods. Confidence scores. The agent can provide confidence scores associated with its predictions, indicating its level of certainty about the answer. Model ensemble. Use multiple Vertex AI vision models for image analysis and combine their outputs to provide a more robust and reliable answer. Challenges and fixes. Challenge 1. Incorrect or incomplete answers. The agent may sometimes generate inaccurate or incomplete answers due to limitations in the Vertex AI vision model or the language model's ability to understand the question. Sample use case. A user asks what color is the car? About an image containing a red car. But the agent responds the car is blue. Fixes. Train the Vertex AI vision model on a data set that includes a wider range of image content, including different colors and object types. Fine-tune the language model on a corpus of questions and answers related to image analysis. Challenge 2. Ambiguous or open-ended questions. The agent may struggle to answer questions that are ambiguous or open-ended, as it may lack sufficient information to provide a definitive answer. Sample use case. A user asks what is happening in this picture? About an image with multiple people interacting. Fixes. Employ a more advanced language model capable of understanding complex and nuanced questions. Use additional knowledge sources, such as external APIs or knowledge graphs, to provide context and information beyond the image itself. Challenge 3. Handling images with complex scenes. The agent may have difficulty analyzing images with complex scenes, where multiple objects and actions are happening simultaneously. Sample use case. A user asks what are the people doing? About an image depicting a crowded street scene. Fixes. Use a Vertex AI vision model that specializes in object detection and scene understanding. Employ techniques like object tracking and relationship analysis to better understand interactions between objects and people in the scene.